Hello there. Welcome to Relax with Science, where the intricate poetry of the universe lulls you to sleep. Before you had a name, before you had a face, before you had even a single memory, you had a rhythm. It began in the quiet dark, just 21 days after you came into being, a tiny, microscopic pulse within a cluster of cells, no larger than a grain of rice. Since that moment, it has not stopped. Not for a single hour of your childhood, not through the long years of your growth, and not for 1 second of the day you have just completed. Right now, as you lie here, and the world outside begins to fade into a soft blur, that same rhythm continues. It is the most loyal companion you will ever have. Squeezing, releasing, filling. A steady, patient drumming that anchors you to the present moment. Whether it beats 60 times a minute or 50, the number is less important than the constancy. It is the sound of your life sustaining itself while you simply let go. We often describe the cardiovascular system in the cold language of engineering: a pump, a network of pipes, a mechanical circuit. And while the heart is indeed a masterpiece of endurance, the engineering description misses the most beautiful part: this system is alive. These are not static pipes, they are living tissues that breathe and react, dilating with a sigh, or constricting in a moment of focus. They respond to the chemistry of your emotions and the physical demands of your dreams. The heart is not just a pump, but an organ with its own internal electricity, its own hormonal wisdom, and an incredible capacity to reshape itself to the life you choose to lead. It is a delivery network that doesn't just carry oxygen. It remembers, it adapts, and in its own silent way, it feels. Tonight, we are going to move through this internal map together. We will drift through the chambers of the heart and watch the electrical cascade that drives every beat. We will explore the vast architecture of the vessels and the elegant physics of flow. We will meet the red blood cells carrying their precious cargo of oxygen, the white cells standing guard, and the extraordinary endothelium, aligning only 1 cell thick, that serves as one of the most sophisticated sensing organs in your body. All of this is happening inside you at this very moment. To understand it is to find one of the quietest forms of wonder, to realize what your body is doing for you in the dark, and to find in that knowledge not worry, but a deep sense of gratitude. This is Relax with Science, and tonight we are going to travel somewhere remarkable together, slowly, gently, with nowhere else to be. We are going into the biology of the beating heart and the vessels that reach every corner of your being, from the crown of your head to the tips of your toes. Let the room grow heavy. Let your breath slow. And if you place your hand over your chest for just a moment, you will feel exactly what we are going to talk about. Steady, patient, already at work, already in its way, extraordinary. I wonder where you are as you listen to this, whether your room is filled with the silence of the night or the distant hum of a city. I wonder if your heart has already begun to slow since you arrived here, finding its rest as the day's demands release their grip. If you feel like it, tell me in the comments where in the world you are tonight. Just a city, a time, or perhaps how the air feels against your skin. I read every one. It means something to me that you are there. If these words bring you any rest tonight, any ease in the body or the mind, a quiet like on the video is a gentle and generous way to say so, and it helps relax with science find its way to someone else who might be lying somewhere in the dark, needing exactly this company. If you know someone who carries the weight of a hard day to bed, consider sending this to them. No explanation needed, just the link. And if there is ever something that could be softer, slower, or more beautiful about what we make here, I want to hear it. This channel belongs to the person lying in the quiet. It has always been made for you. The human heart beats approximately 100,000 times per day, pumping roughly 5 liters of blood per minute at rest, and more than 25 liters per minute during maximal exercise, a range of 5-fold or greater that no engineered pump of comparable size has come close to matching across the same operational lifespan. The arithmetic of the heart across a lifetime is one of those calculations that produces a number too large for ordinary comprehension, so let us approach it in pieces. At a resting rate of 70 beats per minute, a reasonable average across a population of adults, the heart beats approximately 100,000 times per day, 400,000 times per 4 days, approximately 36 million times per year. In a life of 70 years, that is approximately 2.5 billion beats. Not 2.5 billion approximately, 2.5 billion. Each one a complete cycle of filling and emptying, each one driven by an electrical signal that propagates across the heart muscle in a wave of depolarization that is, in its molecular basis, as complex as anything the body produces. And this engine, this extraordinary engine, begins beating in the 3rd week of embryonic development, when the embryo is only a few millimeters long, when most of the structures that will eventually make up a functioning human body have not yet formed. It begins because the cardiac precursor cells, descended from the mesoderm, have developed the capacity for spontaneous electrical depolarization, before any nervous system exists to instruct them. The heart does not wait for permission. It begins. And it continues through every night of dreamless sleep, and every hour of work, and every decade of life, without any instruction more direct than the internal clock that has been running since the first contraction. At rest, it moves 5 liters per minute, the entire blood volume of the body, passing through the circulation approximately once per minute. During vigorous exercise, this output rises to 25 liters or more. In trained athletes, a 5-fold increase, achieved through simultaneous increases in heart rate and stroke volume. No industrial pump of any size maintains this range of output continuously for 70 years without maintenance. The heart, in its endurance, its adaptability, and its fidelity, is without engineering equivalent. The heart is divided into 4 chambers: the right atrium, right ventricle, left atrium, and left ventricle, arranged in 2 functionally separate but anatomically joined pumps that together drive the 2 circulations of the body: the pulmonary circulation through the lungs and the systemic circulation through the rest of the body. The 4-chambered heart of birds and mammals is an evolutionary achievement, one that distinguishes these classes from the simpler 2- and 3-chambered hearts of fish and most reptiles, and whose functional superiority lies in the complete separation of oxygenated and deoxygenated blood. The right side of the heart, the right atrium and right ventricle, receives the deoxygenated blood, returning from the systemic circulation through the great veins, the superior and inferior vena cava, and pumps it through the pulmonary artery into the lungs. The left side, the left atrium and left ventricle, receives the oxygenated blood, returning from the lungs through the pulmonary veins, and pumps it through the aorta into the systemic circulation. These 2 pumps share the interventricular septum, the muscular wall between the ventricles, and beat synchronously, driven by the same electrical signal. The right ventricle generates the lower pressures required to push blood through the low resistance pulmonary circulation, typically 25 millimeters of mercury at peak pressure. The left ventricle generates the higher pressures required to push blood through the high resistance systemic circulation, typically 120 millimeters of mercury at peak pressure, which explains why the left ventricular wall is approximately 3 times thicker than the right. The atria are receiving chambers, filling during ventricular contraction, and then contributing their contents to the ventricles in the final phase of diastole, the atrial kick, that tops up ventricular filling before the next contraction. For chambers, 2 circulations, 1 synchronized pump, and at the boundaries between each chamber and between each chamber and its outflow vessel, a valve, 4 valves in all, ensuring that the flow moves in one direction only. The electrical system of the heart, beginning with the sinoatrial node in the right atrium, through the atrioventricular node, and the bundle of His, through the bundle branches, and the Purkinje fibers, to the ventricular myocardium, is the pacemaking and conduction system that coordinates the mechanical contraction of the heart in a precise, ordered sequence. The electrical system of the heart is a story of organized delay. The sinoatrial node, a small cluster of specialized cardiomyocytes in the upper wall of the right atrium, approximately 10 to 20 millimeters long, supplied by the sinus node artery, is the heart's natural pacemaker, generating electrical impulses spontaneously at a rate of 60 to 100 per minute in the resting adult. The impulse spreads across the atrial myocardium as a wave of depolarization, causing the atria to contract and pump their contents into the ventricles. At the boundary between the atria and ventricles, the atrioventricular junction, the electrical wave encounters the AV node, another cluster of specialized cells whose conducting properties are fundamentally different from the working myocardium. The AV node delays the signal by approximately 120 to 200 milliseconds. This delay is essential. It ensures that the atria have finished contracting and have completed their contribution to ventricular filling before the ventricles begin to contract. A contraction sequence without this delay, with atria and ventricles firing simultaneously, would be mechanically much less efficient. From the AV node, the signal travels rapidly through the bundle of His, a compact tract of specialized conducting tissue running through the interventricular septum, and then splits into the left and right bundle branches that travel along each side of the septum, and finally fans out into the Purkinje fiber network, a mesh of rapidly conducting fibers that distributes the electrical signal to the ventricular myocardium from the apex upward, ensuring that contraction begins at the tip of the heart and progresses upward toward the outflow tracts, efficiently squeezing blood toward the pulmonary artery in the aorta. The cardiac action potential, the electrical event that triggers each heartbeat, differs fundamentally from the neuronal action potential in having a prolonged plateau phase lasting 200 to 300 milliseconds, a property that prevents the tetanic summation that would be catastrophic in cardiac muscle and ensures that each contraction is discrete and separated from the next. The action potential of a ventricular cardiomyocyte is, in its shape and duration, one of the most distinctive electrical signals in the body. A neuronal action potential, the rapid depolarization and repolarization of a nerve cell, lasts approximately 1 to 2 milliseconds. A skeletal muscle action potential lasts approximately 5 milliseconds. A ventricular cardiomyocyte action potential lasts approximately 200 to 300 milliseconds, roughly 100 times longer. This dramatic prolongation is not incidental, but fundamental to cardiac function. In skeletal muscle, The brief action potential is followed almost immediately by the ability to fire again. The refractory period is short, and at high stimulation frequencies, successive contractions can summate, producing the sustained maximal contraction of tetanus. Tetanus in skeletal muscle is mechanically useful. It allows muscles to produce graded, sustained forces. Tetanus in cardiac muscle would be fatal. A hard and sustained tetanic contraction would stop pumping blood entirely. The prolonged plateau phase of the cardiac action potential prevents this. During the 200 to 300 milliseconds of the plateau, maintained by the inward L-type calcium current, the ventricular cardiomyocyte is absolutely refractory. It cannot fire another action potential, regardless of the stimulus. By the time the plateau ends and the cell repolarizes, the mechanical contraction is nearly complete, and the ventricle has ejected its blood. The next action potential cannot begin until the heart is ready to fill again. The plateau is protection. It is the cardiac action potential, insisting on the rest, that makes the next beat possible. The stroke volume, the amount of blood ejected by the ventricle with each beat, is determined by three factors: preload, the degree of ventricular filling before contraction; afterload, the pressure against which the ventricle must contract; and contractility, the intrinsic force-generating capacity of the ventricular myocardium. And the Frank-Starling mechanism ensures that increased filling automatically increases stroke volume. The Frank-Starling mechanism, named for Otto Frank and Ernest Starling, who described its components in the late 19th and early 20th centuries, is perhaps the most elegant intrinsic regulatory mechanism of the heart. Starling's law of the heart states that, within physiological limits, the force of ventricular contraction is proportional to the initial length of the cardiac muscle fibers, that is, to the degree of ventricular filling at end diastole. The cellular basis of this mechanism involves the length-tension relationship of the sarcomere. At longer sarcomere lengths, the overlap between actin and myosin filaments is more optimal, and the calcium sensitivity of the contractile apparatus is higher, so more crossbridges form and more force is generated. The result is that when more blood returns to the heart, as happens during exercise, when increased muscular pumping drives more venous return, the heart automatically contracts more forcefully and ejects more blood. The heart matches its output to its input without requiring any neural instruction. This is the Frank-Starling mechanism in physiological action, and it is part of what allows the heart to handle the moment-to-moment imbalances in venous return that occur during normal activity, the brief augmentation of venous return that accompanies a deep breath, for instance, or the positional change from standing to lying, with automatic compensation and without requiring the nervous system to issue moment-to-moment corrections. Preload, the degree of filling, is one determinant of stroke volume. Afterload, the resistance against which the ventricle must eject, is another, Higher afterload reduces stroke volume by making it harder for the ventricle to empty. Contractility, the intrinsic state of the myocardium, independent of loading conditions, is the third, and it is the property that is altered by the sympathetic nervous system, by calcium sensitizing drugs, and by the pathological changes of heart failure. The coronary arteries, the vessels that supply the heart muscle itself with oxygen and nutrients, arise from the base of the aorta, immediately above the aortic valve, and their anatomy, and the diseases that affect them, are the most clinically consequential in cardiovascular medicine, with coronary artery disease remaining the leading cause of death worldwide. The heart is the organ that supplies oxygen to every other tissue in the body, and it is itself critically dependent on its own blood supply, the coronary circulation, for the oxygen that fuels its continuous mechanical work. The left main coronary artery, arising from the left coronary sinus of the aorta, divides within the first centimeter into the left anterior descending artery, which runs down the front of the heart, supplying the anterior wall of the left ventricle, and the interventricular septum, and the left circumflex artery, which curves around the left side of the heart, supplying the lateral and posterior walls. The right coronary artery, arising from the right coronary sinus, runs in the right atrioventricular groove, supplying the right ventricle, and, in most people, the inferior wall of the left ventricle, and the posterior septum, and crucially, supplying the sinoatrial node and the atrioventricular node in the majority of people, making its obstruction a cause of both myocardial infarction and cardiac arrhythmia. The coronary arteries are end arteries. Their branches do not form the extensive collateral networks that allow other tissues to survive the occlusion of one vessel by rerouting flow from another. Obstruction of a coronary artery produces ischemia and, if sustained, infarction, the irreversible death of the myocardium, supplied by that vessel, because there is no alternative route for the blood to reach those cells. The heart's tolerance for ischemia is measured in minutes. The brain can survive ischemia for approximately 4 minutes before irreversible damage begins. The heart's threshold is approximately 20 minutes before infarction begins in the most ischemia-sensitive subendocardial cells. The coronary arteries are the heart's lifelines. Their disease, the atherosclerotic plaques that progressively narrow their lumens, and the thrombi that can suddenly occlude them, is what kills more people than any other pathological process. Blood pressure, the force per unit area exerted by the blood against the vessel wall, typically measured at 2 points in the cardiac cycle, as systolic and diastolic pressure, is the product of cardiac output and peripheral vascular resistance, and its regulation involves the integrated activity of the heart, the blood vessels, the kidneys, the nervous system, and the endocrine system. 120/80 millimeters of mercury, the traditional standard of normal blood pressure, is actually 2 measurements compressed into a fraction. The systolic pressure of 120 reflects the peak arterial pressure during ventricular contraction, when the pulse of blood ejected into the aorta generates its maximum wall force. The diastolic pressure of 80 reflects the residual arterial pressure during ventricular relaxation, maintained by the elastic recoil of the aortic walls and the peripheral resistance of the arterioles that prevent the pressure from falling to zero between beats. The difference between the two, 40 millimeters of mercury in this example, is the pulse pressure, which is felt at the wrist or the neck as the pulse. The fundamental determinant of mean arterial pressure, the average pressure across the cardiac cycle, is the product of cardiac output and peripheral vascular resistance. To raise blood pressure, the body can either increase cardiac output by raising heart rate or stroke volume, or increase peripheral resistance by constricting the arterioles. To lower it, it can decrease either. The arterioles are the primary site of peripheral resistance regulation, their smooth muscle tone, governed by the autonomic nervous system, by circulating hormones including angiotensin II and adrenaline, and by locally produced vasoactive substances, determines the caliber of these tiny vessels, and therefore the resistance they offer to blood flow. The kidneys regulate blood pressure over the longer term by governing blood volume through salt and water retention. More sodium and water retained produces a larger blood volume, which increases venous return and cardiac output, raising blood pressure. The complexity of blood pressure regulation, involving so many systems acting simultaneously, explains both why hypertension is so difficult to eliminate with a single drug, and why so many different drug classes can be effective in treating it. The cardiac cycle, the sequence of electrical and mechanical events that constitutes a single heartbeat, is divided into diastole, when the ventricles relax and fill, and systole, when the ventricles contract and eject blood, with the entire cycle lasting approximately 800 milliseconds at rest, and shortening to as little as 250 milliseconds during maximal exercise. The cardiac cycle is a precisely timed sequence that must accommodate the conflicting requirements of adequate filling and adequate ejection across a heart rate range of 50 to 200 beats per minute or more. At a resting heart rate of 75 beats per minute, the cycle lasts approximately 800 milliseconds, divided approximately into 500 milliseconds of diastole and 300 milliseconds of systole. Diastole begins with the closure of the aortic and pulmonary valves, which produces the second heart sound, the dub of lube-dub, and is followed by the isovolumetric relaxation phase, during which the ventricular pressure falls rapidly, while the valves are all closed. When ventricular pressure falls below atrial pressure, the mitral and tricuspid valves open, and passive ventricular filling begins, the rapid early filling phase, driven by the pressure gradient and by the elastic recoil of the ventricle that had been compressed during systole. After the passive filling phase, the ventricle and atrium reach pressure equilibrium, and filling slows, the diastasis phase. Atrial systole then adds the final increment of ventricular filling, the atrial kick, which accounts for approximately 15 to 20% of end diastolic volume at rest, but becomes more important when the diastolic filling time shortens at high heart rates. Systole begins with the closure of the mitral and tricuspid valves, producing the first heart sound, an isovolumetric contraction, during which ventricular pressure rises sharply, with all valves closed. When ventricular pressure exceeds aortic and pulmonary artery pressure, the outflow valves open and ejection begins. Ejection is rapid initially, driven by the pressure gradient, and then decelerates as the gradient narrows. When ventricular pressure falls below aortic pressure, the aortic valve closes, beginning the next diastole. The cycle is complete. Here is the next section of your cardiovascular.txt script. The same rigorous 5 to 9 word rhythmic pacing has been applied using commas and em-dashes, and not a single word has been changed, added, or removed. Studio Microphone Processed Script for Microsoft Clipchamp, Part 2. The endothelium, the single layer of cells lining the interior surface of all blood vessels, is one of the largest organs in the body by surface area, covering approximately 600 square meters in the average adult, and is now understood to be a dynamic, secretory organ that regulates vascular tone, coagulation, inflammation, and vascular permeability, rather than a passive lining. The endothelium was, for most of the history of medicine, regarded as a passive barrier, a smooth surface that reduced friction for flowing blood and prevented it from coming into contact with the prothrombotic tissues beneath. This view was completely overturned by the discoveries of the latter half of the 20th century, which revealed the endothelium as one of the most metabolically active and functionally important tissues in the body. The endothelial cells, of which there are approximately 600 billion in a typical adult, arranged in a monolayer 1 cell thick, cover every surface that blood encounters, from the great vessels to the tiniest capillaries. They respond to the mechanical stimulus of blood flow, the sheer stress of the flowing blood on the endothelial surface, by releasing nitric oxide, the potent vasodilator that relaxes the underlying smooth muscle and reduces vascular resistance. They respond to inflammatory signals by expressing adhesion molecules that capture circulating monocytes and neutrophils, initiating the inflammatory process in response to injury or infection. They regulate the balance between coagulation and fibrinolysis by producing both procoagulant factors and anticoagulant proteins, maintaining the blood in a state of fluid but coagulable readiness. They control the permeability of the capillary wall, the degree to which water, proteins, and cells can move between the blood and the surrounding tissues through the regulation of the tight junctions between adjacent cells. The endothelium is the body's interface between the blood and the tissues, and the quality of this interface, healthy, responsive, producing its vasodilating and anticoagulant and anti-inflammatory mediators, is one of the fundamental determinants of cardiovascular health. The aorta, the great artery arising from the left ventricle, and the origin of every systemic artery in the body, is not simply a passive conduit, but a highly elastic vessel, whose walls store energy during systole and release it during diastole, dampening the pulsatile ejection of the heart into a more continuous flow in the peripheral circulation. The aorta's elastic properties, provided by the extraordinary abundance of elastin in its wall, far greater than in any other artery, serve a function that is as important mechanically as it is biologically. With each heartbeat, the left ventricle ejects approximately 70 milliliters of blood into the aorta during the approximately 300 milliseconds of systole. If the aorta were a rigid tube, this ejection would create a very high systolic pressure, and then, during diastole, flow would cease entirely. The pulsatile flow that would result would be poorly tolerated by the delicate capillaries of the peripheral organs. Instead, the elastic aorta acts as a capacitor. It expands during systole, storing some of the stroke volume as potential energy in its stretched wall, and then recoils during diastole, releasing that stored energy to continue driving flow, even as the heart rests. The result is that the pulsatile cardiac output is converted into a more continuous, dampened flow by the time it reaches the small arteries and capillaries of the periphery. This Wynne-Kessel effect, named for the air chamber used in old fire pumps to smooth the pulsatile output of the piston, reduces the peak systolic pressure and maintains the diastolic pressure above zero, protecting the peripheral vasculature from the mechanical stress of large pressure swings. The loss of aortic elasticity with age, as the elastin fibers are progressively cross-linked and calcified, is one of the primary mechanisms of age-related systolic hypertension. The stiffened aorta can no longer buffer the stroke volume, and the systolic pressure rises, while the diastolic pressure may fall, widening the pulse pressure in a characteristic pattern of isolated systolic hypertension. The capillaries, the smallest and most numerous blood vessels, with walls only 1 endothelial cell thick and a lumen diameter of approximately 5 to 10 micrometers, are the sites of all exchange between the blood and the tissues, and their total surface area of approximately 500 square meters is the functional interface of the cardiovascular system. The capillary is, in functional terms, the reason the entire cardiovascular system exists. The heart's extraordinary mechanical work, the elaborate architecture of the large vessels, the precise regulation of pressure and flow, all of it is in the service of ensuring that, at every tissue in the body, there are capillaries through which the blood flows slowly enough and close enough to the surrounding cells to exchange oxygen, glucose, amino acids, and hormones for carbon dioxide, metabolic waste, and cellular products. A capillary is the simplest vascular structure in the body, a tube approximately 5 to 10 micrometers in diameter, barely wide enough for a red blood cell, which at approximately 8 micrometers in diameter, must deform slightly to squeeze through the smallest capillaries, formed by a single layer of endothelial cells, resting on a basement membrane, surrounded in many organs by the end feet of astrocytes, or parasites that regulate permeability and tone. The wall of a capillary is, in its entirety, this one-cell layer, a thickness of approximately half a micrometer, through which oxygen diffuses from the hemoglobin of passing red blood cells into the interstitial fluid, and thence into the cytoplasm of surrounding cells, and through which carbon dioxide diffuses in the opposite direction. The total surface area of this interface, 500 square meters in an average adult, the area of half a tennis court, is achieved by the extraordinary density of the capillary network in highly metabolically active tissues, like the myocardium. Every cardiomyocyte is within 10 micrometers of a capillary. This proximity is not an accident, but a precise developmental achievement. The growth of new capillaries, angiogenesis, is driven by oxygen-sensing mechanisms in the tissues, such that hypoxic tissues produce VEGF and other angiogenic factors that stimulate the endothelium to sprout new capillaries until every cell is adequately supplied. The cardiac valves, the mitral and tricuspid valves, between the atria and ventricles, and the aortic and pulmonary valves, between the ventricles and the great arteries, open and close passively, in response to pressure gradients across them, and the sounds they produce on closing constitute the heart sounds audible with a stethoscope. The 4 cardiac valves are passive, pressure-operated structures. They do not have muscles that open and close them, but instead respond to the pressure differentials that develop across them as the cardiac cycle progresses. The mitral valve, between the left atrium and the left ventricle, and the tricuspid valve, between the right atrium and the right ventricle, are atrioventricular valves, attached at their margins to the fibrous annulus of the atrioventricular junction, and at the tips of their leaflets to the papillary muscles of the ventricle wall, through the chordae tendineae, the tendinous strings that prevent the leaflets from prolapsing back into the atrium during the high pressures of ventricular systole. The valve leaflets open when atrial pressure exceeds ventricular pressure during diastole, and close when ventricular pressure rises above atrial pressure during systole, the chordae holding them shut against the pressure. The aortic and pulmonary valves are semilunar valves, 3 crescent-shaped cusps that open when ventricular pressure exceeds the pressure in the great artery, allowing ejection, and snap shut when the ventricular pressure falls below aortic or pulmonary pressure at the end of systole, preventing backflow. The first heart sound, the low-pitched lube, is produced by the closure of the mitral and tricuspid valves at the onset of systole. The second heart sound, the shorter, higher-pitched dub, is produced by the closure of the aortic and pulmonary valves at the end of systole. These sounds, audible with a stethoscope and by pressing the ear or a hand to the chest, are the mechanical signature of each cardiac cycle, the valves announcing their closing, the heart reporting that it has fired. The red blood cell, the erythrocyte, is the most numerous cell in the body, with approximately 25 trillion circulating in the average adult, and its extraordinary specialization for oxygen transport, including the abandonment of its nucleus and mitochondria to maximize hemoglobin content, is one of the most radical cellular specializations in mammalian biology. The red blood cell is, in some sense, a cell that has sacrificed almost everything a cell normally is, in order to become as efficient as possible at one thing: carrying oxygen. In the course of its maturation, from a nucleated respiratory to the mature erythrocyte that circulates in the blood, the developing red cell ejects its nucleus, an unprecedented act for a mammalian cell, and digests its mitochondria, ribosomes, and most other organelles. What remains is essentially a membrane sac containing hemoglobin, the iron-containing protein that binds oxygen, in a concentration of approximately 33 grams per 100 milliliters, as high as is compatible with the cell remaining liquid rather than crystalline. The biconcave disc shape that results from this radical simplification serves a functional purpose. It provides a high surface area to volume ratio that maximizes the diffusion path for oxygen, and it gives the cell the mechanical flexibility required to deform and pass through the smallest capillaries. A mature red cell contains approximately 270 million molecules of hemoglobin, each capable of carrying 4 molecules of oxygen, giving the cell a potential oxygen carrying capacity of approximately 1 billion molecules of oxygen, approximately 30 times the oxygen that would dissolve in the same volume of plasma. This specialization is so complete that the red cell has no capacity for protein synthesis. It cannot repair itself or adapt to changing conditions, and it lives for approximately 120 days, after which it is removed from the circulation by the spleen and liver, its hemoglobin recycled, and its membrane fragments cleared. Hemoglobin, the iron-containing protein that occupies approximately 33% of the red blood cell's interior, binds oxygen cooperatively, meaning that the binding of the first oxygen molecule to hemoglobin increases the affinity for the next, and the resulting sigmoidal oxygen dissociation curve allows hemoglobin to load oxygen efficiently in the lungs and unload it efficiently in the tissues. Hemoglobin is a tetramer for polypeptide chains, each containing a heme group whose central iron atom can bind 1 molecule of oxygen. In adults, the predominant form consists of 2 alpha chains and 2 beta chains. The cooperative binding behavior of hemoglobin, the property that distinguishes it from the simpler, non-cooperative binding of myoglobin, arises from a structural transition. The first oxygen binds with relatively low affinity to the deoxygenated 10th state of the molecule, But this binding shifts the molecule toward a relaxed conformation, in which the remaining heme groups are more accessible and bind oxygen with higher affinity. The result is the characteristic S-shaped, sigmoidal oxygen-hemoglobin dissociation curve, which has two physiologically critical properties. At the high partial pressure of oxygen in the pulmonary capillaries, approximately 100 millimeters of mercury, the sigmoidal curve places hemoglobin near the flat top of its saturation curve, where it is approximately 97% saturated with oxygen. A large fall in oxygen partial pressure in the lungs produces only a small fall in saturation. Hemoglobin is well loaded, even in the face of modest pulmonary hypoxia. In the tissues, where the partial pressure of oxygen is much lower, approximately 20 to 40 millimeters of mercury, hemoglobin falls to the steep part of its dissociation curve, where small further reductions in oxygen partial pressure produce large releases of oxygen. Hemoglobin unloads oxygen efficiently in the tissues. The curve also shifts rightward in the tissues, in the direction of reduced oxygen affinity, in response to increased carbon dioxide, increased acidity, increased temperature, and increased 2,3-bisphosphoglycerate, all of which are present in metabolically active tissues. The Bohr effect thus delivers more oxygen to the tissues that are working hardest. The lymphatic system, the network of vessels, nodes, and organs that returns excess interstitial fluid to the venous circulation and serves as the highway of the immune system, is closely coupled to the cardiovascular system and handles the approximately 3 liters of fluid per day that leak from the capillaries into the tissue spaces. The lymphatic system is, in its mechanical function, the overflow management system of the cardiovascular circulation. As blood flows through capillaries, the hydrostatic pressure of the blood and the osmotic forces across the capillary wall drive a net filtration of fluid from the capillary into the interstitial space, approximately 20 liters of fluid per day in the average adult. Of this, approximately 17 liters is reabsorbed back into the venous end of the capillaries through osmotic forces as the blood, now more concentrated after losing fluid at the arterial end, draws water back in. The remaining approximately 3 liters, which has picked up proteins and cellular debris, and sometimes immune cells, in its passage through the interstitium, enters the blind-ended lymphatic capillaries that begin in the tissue spaces of virtually every organ. These lymphatic capillaries drain into progressively larger lymphatic vessels that have their own endothelial lining and their own system of valves, similar to venous valves, that prevent backflow. The lymph is propelled forward by the rhythmic compression of the lymphatic vessels, by surrounding skeletal muscle and arterial pulsations, augmented by the pumping action of the smooth muscle in the larger lymphatic vessel walls. The lymph passes through lymph nodes, the filtering stations of the lymphatic system, containing dense populations of lymphocytes and macrophages, before draining into the thoracic duct and the right lymphatic duct, which empty into the left and right subclavian veins respectively, returning the fluid to the venous circulation. Disruption of the lymphatic system by infection, by tumor invasion of lymph nodes, by surgical lymph node removal, produces lymphedema, the accumulation of protein-rich fluid in the tissues, because the overflow system has been compromised. Atherosclerosis, the progressive accumulation of lipid-laden plaques in the walls of medium and large arteries, is not simply a passive process of fat deposition, but an active inflammatory disease of the vessel wall, driven by the interaction of oxidized LDL cholesterol, endothelial dysfunction, and macrophage activation, in a process that begins in childhood and takes decades to produce clinical events. The modern understanding of atherosclerosis as an inflammatory disease, rather than the passive deposition of fat in pipes that the older plumbing metaphor implied, has transformed the approach to its prevention and treatment. The process begins when circulating LDL cholesterol particles, particularly when oxidized or otherwise modified, enter the intima of the arterial wall, the space between the endothelium and the smooth muscle media, and are taken up by macrophages that have been recruited to the intima by inflammatory signals from the endothelium. The macrophages engulf the oxidized LDL through scavenger receptors, receptors that are not downregulated by intracellular cholesterol accumulation, unlike the normal LDL receptor, and progressively become laden with cholesterol, transforming into foam cells. The accumulation of foam cells in the intima forms the fatty streak, the earliest visible lesion of atherosclerosis, which can be found in the aortas of children and young adults at autopsy. Over years and decades, the fatty streak evolves into the fibrofatty plaque, a core of lipid and necrotic foam cells, covered by a fibrous cap of smooth muscle cells, and collagen secreted by smooth muscle cells that have migrated from the media into the intima. This fibrous cap is the structural element that determines the plaque's vulnerability. A thick, well-organized cap is resistant to rupture, while a thin cap with a large lipid core is vulnerable. When a vulnerable plaque ruptures, the thrombogenic lipid core is exposed to the blood, triggering the coagulation cascade and the formation of a thrombus that can suddenly occlude the coronary artery, the acute myocardial infarction. The plaque has been growing silently for decades before this event. The event itself takes minutes. The microcirculation, the arterioles, capillaries, and venules that constitute the smallest vessels of the circulation, is where most of the body's vascular resistance resides, and where the moment-to-moment regulation of blood flow to individual tissues occurs through the active constriction and dilation of arteriolar smooth muscle in response to local metabolic signals. The arterioles, vessels typically between 10 and 100 micrometers in diameter, are the resistance vessels of the circulation, governing the distribution of blood flow among the body's many organs and tissues through their variable state of constriction. The smooth muscle in the arteriolar wall can contract or relax in response to an extraordinary variety of signals, allowing the local microcirculation to respond to the metabolic needs of the tissue it supplies. When a tissue becomes metabolically active, producing more carbon dioxide, more lactate, more adenosine, consuming more oxygen, these metabolic byproducts accumulate locally in the interstitial fluid and directly relax the arteriolar smooth muscle, increasing blood flow to the active tissue and delivering more oxygen. This local metabolic control, sometimes called functional hyperemia, is the primary mechanism by which working muscle receives its increased blood flow during exercise, by which the gut increases its perfusion during digestion, and by which neural activity in a specific brain region increases blood flow to that region, the coupling exploited by functional MRI to map brain activity. Heart rate variability, the beat-to-beat variation in heart rate that reflects this continuous autonomic modulation, is a marker of the health of the autonomic nervous system's cardiac control. High variability indicates a well-functioning, responsive autonomic system, while low variability is associated with increased cardiovascular risk and is a feature of autonomic neuropathy, heart failure, and the aftermath of myocardial infarction. The blood coagulation cascade, the enzymatic amplification system that converts soluble fibrinogen into the insoluble fibrin clot that seals vascular injuries, involves approximately 13 plasma proteins in two converging pathways, the intrinsic and extrinsic, that together produce the explosive thrombin generation needed for rapid hemostasis. The coagulation cascade is one of the most elegantly engineered amplification systems in biology. The problem it solves is one of timing and magnitude. A vascular injury can be large or small, and it must be sealed before blood loss becomes critical, but the clot must also be precisely localized to the site of injury to avoid the thrombosis of normal vessels. The cascade achieves this through a series of enzymatic activation steps, in which each active enzyme activates many molecules of the next enzyme in the chain, a geometric amplification that converts the initial signal of vascular injury into a massive local production of thrombin, the central enzyme of coagulation, which converts fibrinogen to fibrin. The extrinsic pathway, now called the tissue factor pathway, is initiated when vascular injury exposes tissue factor, a membrane protein expressed in subendothelial cells, but not normally in contact with the blood. Tissue factor binds factor VIA, and this complex activates factor X directly. The intrinsic pathway, the contact pathway, is activated by the exposure of negatively charged surfaces, such as collagen, and involves the sequential activation of factors 12, 11, 9, and 8 before activating factor X. Both pathways converge on the activation of factor X, which with its cofactor VA produces the prothrombinase complex that converts prothrombin to thrombin. Thrombin is the central effector. It cleaves fibrinogen to fibrin, activates the platelets that have already adhered to the injury site, and activates factor 13 that cross-links the fibrin polymer into a stable, insoluble clot. The entire cascade, from initial vascular injury to a stable clot, can be completed in as little as 2 minutes, driven by the geometric amplification of each step. The baroreceptors, stretch-sensitive nerve endings in the walls of the carotid sinus and the aortic arch, provide the afferent limb of the baroreflex, the most important short-term blood pressure regulating reflex, whose efferent response through the cardiovascular centers of the medulla adjusts heart rate, stroke volume, and vascular tone within seconds to buffer changes in arterial pressure. The baroreflex is the heart and circulation's rapid response stabilization system, a negative feedback loop that detects changes in arterial pressure and generates the appropriate cardiovascular adjustments within seconds, maintaining pressure in the range required for adequate cerebral and coronary perfusion. The carotid sinus baroreceptors, located in the wall of the internal carotid artery, just above its origin, and the aortic arch baroreceptors in the aortic wall, are mechanoreceptors, nerve endings that fire in proportion to the degree of vessel wall distension, which reflects arterial pressure. Their afferent signals travel via the glossopharyngeal nerve from the carotid sinus and the vagus nerve from the aortic arch to the nucleus tractus solitarius in the medulla oblongata, which integrates the baroreceptor input and coordinates the efferent cardiovascular response. When arterial pressure rises, by increased blood volume, by increased cardiac output from exercise, or by external mechanical stimulation of the carotid sinus, the baroreceptors fire more rapidly, increasing their inhibitory input to the medullary cardiovascular centers, which respond by increasing parasympathetic outflow to the heart, decreasing sympathetic outflow to the heart and blood vessels, and decreasing adrenal medullary catecholamine release. The net effect is a fall in heart rate, stroke volume, and peripheral resistance, a corrective cardiovascular adjustment that returns pressure toward its set point. The converse applies to a fall in pressure. Reduced baroreceptor firing reduces inhibitory input, sympathetic activation increases, and pressure is restored. The entire reflex operates on a timescale of seconds, making it capable of buffering the rapid blood pressure changes, of postural transitions and brief physical exertions. The pulmonary circulation, the circuit of blood flow from the right ventricle through the lungs and back to the left atrium, is a low-pressure, low-resistance system with unique properties including hypoxic pulmonary vasoconstriction, which shunts blood away from poorly ventilated lung regions to optimize ventilation perfusion matching. The pulmonary circulation is the cardiovascular system's most physiologically unusual circuit. Its driving pressure, the pressure difference between the pulmonary artery and the left atrium, is approximately 15 millimeters of mercury, approximately 1/7 of the pressure, driving the systemic circulation. Yet it must carry the same cardiac output as the systemic circulation, which means its resistance must also be approximately 1/7 that of the systemic circulation. It achieves this through the architecture of the pulmonary vasculature, wide caliber vessels, thin walls, short path lengths, and through the unique ability of the pulmonary arterioles to dilate in response to high blood flow, recruiting additional capillary beds as cardiac output increases. The most distinctive physiological property of the pulmonary circulation is its response to local hypoxia in most of the body. Hypoxia causes vasodilation. The normal response to low oxygen is to increase blood flow to the hypoxic tissue. In the lung, the opposite occurs. Local alveolar hypoxia causes local pulmonary arteriolar constriction, diverting blood away from the poorly ventilated area of lung toward better ventilated regions. This hypoxic pulmonary vasoconstriction is a reflex that optimizes the matching of ventilation and perfusion across the lung, directing blood to the regions that can oxygenate it most efficiently. At high altitude, where the alveolar oxygen tension is low throughout both lungs, hypoxic pulmonary vasoconstriction occurs globally, raising the pulmonary arterial pressure and causing the right ventricular hypertrophy of high-altitude heart disease. This is the price of a reflex that is superbly adapted to local hypoxia, but poorly adapted to global hypoxia. The white blood cells, the leukocytes, including neutrophils, lymphocytes, monocytes, eosinophils, and basophils, travel through the cardiovascular system, not as passive passengers, but as active patrollers that continuously exit and re-enter the circulation, surveying the tissues for infection, injury, and abnormal cells. The 5 billion or so leukocytes in the average adult blood are not simply riding in the circulation, waiting to be called to a site of infection. They are in continuous transit, exiting the blood through the endothelium of post-capillary venules into the tissues, surveying the tissue environment, and returning to the circulation via the lymphatic vessels. The neutrophil, the most numerous white cell, comprising approximately 50 to 70% of circulating leukocytes, has a blood transit time of only 6 to 12 hours before it marginalizes in a post-capillary venule, receives chemokine signals from inflamed or infected tissue, and migrates through the endothelium into the tissue by the process of diapedesis. There, it phagocytoses and kills bacteria by degranulating its toxic contents and generating reactive oxygen species. It has a tissue lifespan of 1 to 2 days before it undergoes apoptosis. The monocyte, circulating for 1 to 3 days, exits the blood and differentiates into the macrophage, the long-lived tissue phagocyte, or in specific contexts into the dendritic cell that presents antigen to lymphocytes. The lymphocytes, T cells and B cells, patrol the secondary lymphoid organs and the peripheral tissues, continuously sampling the antigenic landscape for the presence of pathogens or abnormal cells. The eosinophil and basophil patrol for parasitic infections and participate in allergic reactions. The cardiovascular system is not simply the highway for the immune cell's journey. It is their environment, the medium through which they travel, and the signaling environment, the cytokines and adhesion molecules of the endothelium, that directs their exit and their destination. The phenomenon of cardiac remodeling, the structural and functional changes that the heart undergoes in response to sustained changes in pressure or volume load, allows the heart to adapt to new demands over weeks to months. But the same molecular mechanisms that produce adaptive remodeling in exercise training can produce maladaptive remodeling in heart failure. The heart is a remarkably plastic organ. It can increase its mass, change its geometry, and alter its contractile properties in response to the loads placed upon it over weeks to months. This capacity for remodeling has two distinct expressions. In the athlete's heart, the cardiac adaptation to sustained endurance or resistance training. The remodeling is adaptive. Endurance training produces concentric enlargement of all chambers, with increased wall motion, and a normal or enhanced ejection fraction. A high-performance heart that can pump more blood with each beat. Resistance training produces concentric hypertrophy, increased wall thickness without chamber enlargement, also associated with normal function. Both forms of athlete's heart are beneficial, reflecting the heart's efficient adaptation to increased demand. In heart failure, the same molecular pathways of hypertrophy and remodeling produce an initially compensatory, but ultimately maladaptive response. In response to the increased wall stress of pressure overload, as in hypertension or aortic stenosis, the ventricle undergoes concentric hypertrophy. The wall thickens to normalize wall stress. Initially, this is compensatory, the same principle as the athlete's adaptation to resistance training. But in the pathological context of sustained pressure overload, the hypertrophied myocardium outgrows its blood supply. The molecular program of the hypertrophied cardiomyocyte shifts toward a fetal gene expression pattern. The diastolic function deteriorates as the thick wall becomes stiff, and eventually the compensated hypertrophy gives way to the dilated, failing heart of decompensated systolic heart failure. The same molecular machinery, the calcineurin NFAT and mTOR pathways, that builds the athlete's efficient heart, can, in the wrong context, build the failing heart. The peripheral chemoreceptors, the carotid and aortic bodies, located at the bifurcation of the common carotid artery and in the aortic arch, detect changes in arterial oxygen tension, carbon dioxide, and pH, and generate cardiovascular and respiratory reflex responses that maintain gas exchange during hypoxia and hypercapnia. The carotid body is one of the most remarkable sensory organs in the body, a tiny, highly vascularized structure, weighing approximately 2 milligrams, located at the bifurcation of the common carotid artery, that senses the chemical composition of the arterial blood with extraordinary sensitivity and generates reflex adjustments in breathing and heart rate that maintain oxygen delivery within safe limits. The glomus cells of the carotid body express a family of oxygen-sensitive ion channels, primarily the task channels and KV channels, whose activity is reduced by falls in arterial oxygen partial pressure, causing the cells to depolarize and release dopamine and other neurotransmitters onto the adjacent sensory nerve endings. These endings transmit the chemoreceptor signal via the glossopharyngeal nerve to the nucleus tractus solitarius, which integrates the signal with baroreceptor and other cardiovascular inputs and coordinates the reflex response. The primary cardiovascular response to carotid body activation is bradycardia and peripheral vasoconstriction, but diving reflex-like response that diverts blood to the heart and brain during hypoxia at the expense of the peripheral circulation. The respiratory response, the ventilatory increase that is the more familiar response to hypoxia at altitude, is coordinated by the respiratory centers in the medulla and effectively counters the hypoxia by increasing alveolar ventilation. In heart failure, the carotid body becomes hyperactive, chronically activated by the reduced oxygen delivery and elevated sympathetic tone of the failing circulation, and this hyperactivity is now recognized as a contributor to the excessive sympathetic activation, the periodic breathing, and the impaired exercise tolerance that characterize heart failure. Nitric oxide, produced by the endothelial cells of blood vessels from the amino acid arginine through the action of endothelial nitric oxide synthase, is the primary endothelium-derived vasodilator and one of the most important molecules in cardiovascular physiology, regulating vascular tone, platelet aggregation, and endothelial inflammation. The discovery of nitric oxide as the endothelium-derived relaxing factor, the molecule responsible for the acetylcholine-induced vasodilation that Robert Furchgott described in 1980, and that won him, Louis Ignarro, and Ferit Murad the Nobel Prize in 1998, transformed cardiovascular physiology. Nitric oxide is a gas, a diatomic molecule of nitrogen and oxygen, produced in the endothelial cell by enos, which converts arginine to citrulline and NO. The NO diffuses freely through the endothelial cell membrane into the underlying vascular smooth muscle, where it activates soluble guanylyl cyclase, increasing cyclic GMP production, activating protein kinase G, and ultimately reducing intracellular calcium and causing smooth muscle relaxation and vasodilation. It also diffuses into the blood vessel lumen, where it inhibits platelet aggregation by the same cyclic GMP mechanism, preventing the formation of platelet thrombi on the intact endothelial surface. And it acts in an autocrine fashion on the endothelial cell itself, reducing the expression of adhesion molecules that would otherwise capture circulating monocytes, an anti-inflammatory effect. The production of nitric oxide by the endothelium is stimulated by the shear stress of flowing blood, the mechanical signal of adequate blood flow, and by acetylcholine, bradykinin, and many other agonists. In atherosclerosis and in conditions of endothelial dysfunction, which can result from hypertension, diabetes, hypercholesterolemia, smoking, and aging. Enos activity is reduced, and the bioavailability of nitric oxide falls. The loss of endothelial nitric oxide contributes to vasoconstriction, platelet aggregation, inflammation, and the progression of atherosclerosis, a pathophysiological cascade in which the loss of a single molecule unravels multiple protective mechanisms simultaneously. Myocardial infarction, the death of cardiac muscle cells from sustained ischemia when a coronary artery is occluded, typically by the rupture of an atherosclerotic plaque, and the subsequent thrombosis, triggers a sequence of injury, inflammation, and repair that ultimately replaces the necrotic myocardium with scar tissue and permanently alters the mechanical function of the heart. The events of a myocardial infarction unfold on several timescales. Within seconds of coronary artery occlusion, the affected myocardium ceases its aerobic metabolism. The oxygen supply has been cut. Within minutes, it ceases to contract. The mechanical failure of ischemic myocardium precedes cell death by a considerable margin, which is why the affected region becomes dyskinetic or akinetic before any cells have died. Within 20 to 40 minutes, the most ischemia-sensitive cells, the subendocardial cardiomyocytes, at the inner surface of the ventricular wall, furthest from the epicardial coronary supply, begin to die. The necrosis spreads from the endocardium toward the epicardium over the following hours. The wavefront phenomenon, like a slowly expanding infarct, that can be interrupted at any point by restoration of blood flow. After 6 to 12 hours, the necrosis is typically complete if reperfusion has not occurred. The subsequent inflammatory response, the invasion of neutrophils, followed by macrophages that clear the necrotic debris, occurs over days to weeks, during which the infarcted wall is at its most vulnerable to mechanical complications, rupture of the ventricular free wall, perforation of the interventricular septum, or rupture of the papillary muscles, causing mitral regurgitation. The replacement of the necrotic myocardium by fibrous scar, the remodeling phase, takes weeks to months and results in a wall segment that can no longer contract, and that may bulge during systole, the ventricular aneurysm. The surviving myocardium hypertrophies to compensate for the lost contractile mass, and the ventricle progressively dilates and remodels in a process that can, over years, lead to the diastolic and systolic dysfunction of ischemic cardiomyopathy. The pericardium, the fibrous sac that surrounds and contains the heart, plays important roles in preventing acute cardiac dilation, maintaining the mechanical relationships between the cardiac chambers, and protecting the heart from infection, spreading from adjacent structures, and its inflammation or accumulation of fluid within it can cause clinically significant cardiac compromise. The pericardium is a two-layered fibrocerous sac that encases the heart and the proximal portions of the great vessels. The outer fibrous pericardium is a tough, inextensible structure of dense collagen that resists acute cardiac distension. When the heart acutely dilates due to volume overload or right heart failure, the fibrous pericardium limits the degree of dilation and generates the pericardial constraint that increases the diastolic filling pressures of both ventricles simultaneously. The inner serosal pericardium has visceral and parietal layers, separated by a potential space, the pericardial cavity, containing approximately 15 to 30 milliliters of pericardial fluid that lubricates the movement of the heart within its sac. Pericardial effusion, the accumulation of excess fluid in the pericardial cavity, develops in pericarditis, in malignancy, in hypothyroidism, and in many other conditions, and its hemodynamic significance depends critically on the rate of accumulation rather than the volume. The pericardium's inextensibility means that slow accumulation allows gradual stretch and accommodation of several hundred milliliters without significant hemodynamic compromise, while rapid accumulation of even 100 milliliters can raise the pericardial pressure sufficiently to impair diastolic filling. Cardiac tamponade. In tamponade, the elevated pericardial pressure compresses the cardiac chambers during diastole, reducing ventricular filling and cardiac output, with the characteristic clinical presentation of falling blood pressure, rising venous pressure, and muffled heart sounds, Beck's triad, and the echocardiographic sign of right ventricular diastolic collapse. The pericardium's role as a mechanical constraint, beneficial in chronic volume overload, potentially lethal in acute effusion, reflects the double-edged nature of its inextensibility. Blood viscosity, the resistance of blood to flow, which is determined primarily by the hematocrit and by the concentration of plasma proteins, influences cardiac work and peripheral vascular resistance, and its pathological increase in conditions of polycythemia or hypergammaglobulinemia increases the risk of thrombosis and reduces tissue perfusion. Blood is not water. Its viscosity, approximately 3 to 4 times that of water, under normal conditions, is a significant factor in the resistance to flow that the heart must overcome with each beat, and it is determined primarily by the hematocrit, the fraction of blood volume occupied by red blood cells, and to a lesser extent by the concentration of plasma proteins, particularly fibrinogen and the immunoglobulins. Under normal flow conditions in large vessels, blood behaves approximately as a Newtonian fluid. Its viscosity is essentially constant regardless of flow rate. But in the microcirculation, where the individual behavior of red blood cells becomes significant, blood is non-Newtonian. At low flow rates, red cells aggregate into Rouleau stacks that increase viscosity dramatically, and at high flow rates the cells align and deform in ways that reduce viscosity. The hematocrit's influence on viscosity is nonlinear. At a normal hematocrit of approximately 45%, viscosity is in the optimal range. That balances oxygen carrying capacity against the cardiac work required to pump the more viscous blood. At hematocrits above 60%, As in polycythemia vera, viscosity rises steeply, increasing the risk of thrombosis in the microcirculation and increasing cardiac afterload. At hematocrits below 30%, as in significant anemia, viscosity falls, but the reduced oxygen content of the blood forces a compensatory increase in cardiac output, increasing cardiac work by the volume route rather than the pressure route. The conduction velocity of the cardiac action potential varies markedly between different parts of the conduction system. Fastest in the Purkinje fibers at approximately 4 meters per second, and slowest in the AV node at approximately 0.5 meters per second. And these velocity differences are the basis of the ordered timing of atrial and ventricular activation. The conduction system's velocity hierarchy is as functionally important as the physical structure of the pathways. The slowest conduction in the AV node, created by the small cell size, low intercellular coupling, and depolarization-dependent calcium influx that characterize nodal cells, is the source of the PR interval delay, visible on the electrocardiogram. The time between the onset of atrial depolarization and the onset of ventricular depolarization, normally 120 to 200 milliseconds. This delay, as already described, ensures the completion of atrial contraction before ventricular contraction begins. The fastest conduction in the Purkinje fibers, created by large cell diameter, abundant gap junctions, and the rapid sodium current of these cells, ensures that once the activation wave enters the ventricular myocardium from the Purkinje network, it spreads almost simultaneously across the entire ventricle, producing the near-synchronous activation that underlies the efficient, coordinated squeeze of ventricular systole. The QRS complex of the normal electrocardiogram, lasting approximately 80 to 100 milliseconds, reflects this rapid, synchronous ventricular activation. Disease processes that disrupt the normal conduction pathways: bundle branch block from coronary artery disease, aberrant conduction pathways in Wolff-Parkinson-White syndrome, fibrosis of the conduction system in the aging heart, alter these carefully calibrated timing relationships, producing the widened QRS complexes, the altered activation sequences, and the mechanical dysynchrony of diastolic and systolic dysfunction that result from lost conduction precision. You have been with me for a while now, traveling through the beating heart, and the flowing blood, and the vessels that reach every corner of the body. I find that quietly wonderful. If these nights together mean something to you, if there is something in the pace of this, in the way the biology of the body becomes a kind of company for the later hours, then subscribing to Relax with Science is a simple and warm way to say, yes, I would like more of this. I would like to come back. And I will be here whenever you do. The electrocardiogram, the recording of the electrical activity of the heart from the body surface, was developed by Willem Einthoven, who received the Nobel Prize in 1924 for his work, and remains one of the most information-rich clinical tests in medicine despite its simplicity, capable of diagnosing myocardial infarction, arrhythmias, conduction abnormalities, and electrolyte disturbances from 12 limb and chest leads. The electrocardiogram is one of those medical technologies that seems, in retrospect, to have been waiting to be discovered. So fundamental is the electrical activity it records, so informative the waveforms it produces. Endothelium began his work in the 1890s, using a capillary electrometer, but his development of the string galvanometer, a device in which a fine conducting thread, suspended in a magnetic field, deflects in proportion to the current flowing through it, allowed him to record the cardiac electrical activity with sufficient sensitivity and temporal resolution to capture the P wave, QRS complex, and T wave that bear the same names today as he gave them in 1895. The 12-lead ECG that is standard today records the same electrical activity from 12 different directions, 3 limb leads, 3 augmented limb leads, and 6 precordial chest leads, providing a 3-dimensional picture of the cardiac electrical field that allows the pattern of activation abnormalities to be precisely localized. The inferior leads 2, 3, and AVF look at the inferior wall of the left ventricle, supplied by the right coronary artery. The lateral leads I, AVL, V5, V6 look at the lateral wall, supplied by the circumflex artery. The anterior leads V1 through V4 look at the anterior wall and septum, supplied by the left anterior descending artery. An ST elevation in specific leads identifies not just that a myocardial infarction is occurring, but which coronary artery is occluded, information that guides the urgent catheterization and stenting that can restore flow and salvage myocardium if performed within hours. The blood-brain barrier, whose tight endothelial junctions prevent the passive passage of most circulating substances into the brain parenchyma, is one of the most clinically significant specializations of the cardiovascular endothelium, requiring dedicated transport systems for glucose, amino acids, and other essential nutrients, and creating major challenges for the pharmacological treatment of neurological diseases. The endothelium of the brain's capillaries is qualitatively different from the endothelium of capillaries elsewhere in the body. In most organs, the tight junctions between adjacent endothelial cells are leaky enough to allow water, ions, and small molecules to pass freely between the blood and the interstitial fluid, with the capillary wall serving primarily as a barrier to cells and large proteins. In the brain, the tight junctions are so complete that essentially nothing passes between the endothelial cells. Every molecule that enters the brain must either diffuse through the endothelial cell membrane, possible for small lipid-soluble molecules like oxygen, carbon dioxide, and alcohol, or be transported across the cell by a specific carrier protein, the route for glucose, amino acids, nucleosides, and other essential hydrophilic nutrients. This complete barrier is maintained by the inductive influence of the astrocyte end feet that encase the brain capillaries, signaling to the endothelial cells to maintain their tight junctions through mechanisms that include the WNT signaling pathway and the release of angiopoietin-1. The consequence for pharmacology is that the vast majority of drugs, being water-soluble and too large for free diffusion through the lipid bilayer, cannot enter the brain from the bloodstream, which is why treating brain diseases with systemic medications is so much more difficult than treating diseases of other organs. The blood-brain barrier that protects the neural environment from the fluctuations of blood chemistry simultaneously excludes most drugs that might be effective in treating neurological conditions. The platelets, the smallest formed elements of the blood, produced by the fragmentation of megakaryocytes in the bone marrow at a rate of approximately 150 billion per day, are anucleate cell fragments that, despite their structural simplicity, perform the extraordinarily complex task of primary hemostasis, detecting vascular injury, and rapidly forming the platelet plug that is the first step in wound sealing. Platelets are, in some respects, the most biochemically complex of the blood's formed elements relative to their size. At approximately 2 to 3 micrometers in diameter, and without a nucleus, they might seem too simple for the complex tasks they perform, yet they express hundreds of distinct surface receptors, maintain an elaborate internal membrane system, contain multiple classes of secretory granules packed with regulatory molecules, and can undergo the dramatic shape change and spreading that characterizes activation, all within seconds of encountering the subendothelial matrix exposed by vascular injury. The process of platelet activation begins when platelets flowing in the blood encounter the collagen fibers exposed when the endothelial layer is disrupted. Von Willebrand factor, secreted by endothelial cells and available in the plasma, bridges between the collagen and the platelet surface receptor GPIB9V, slowing the platelet and allowing it to adhere to the injured surface. The adherent platelet is then activated by collagen binding to the GPVI receptor and by locally generated thrombin binding to the PAR receptors on the platelet surface. Activation transforms the platelet from its resting discoid shape to an irregular, spiky sphere with extending pseudopods, and triggers the release of ADP and thromboxane A2 from the platelet granules, potent activators of nearby platelets that recruit additional platelets to the growing platelet plug. The activated platelets also express the integrin GPIIBIIA in its active conformation, allowing cross-linking by fibrinogen between adjacent platelets and consolidating the plug into a stable aggregate. The entire sequence, from initial contact to stable platelet plug, takes place in seconds. The right lymphatic duct and the thoracic duct, the two main collecting ducts of the lymphatic system, empty into the venous circulation at the junctions of the subclavian and jugular veins, returning the 3 liters of daily lymph flow to the blood and completing the cycle of fluid exchange between the blood and the tissues. The thoracic duct is the larger of the two, and the more anatomically significant. It collects lymph from the entire body, below the diaphragm, and from the left side of the thorax, head, and neck, beginning as the cisterna chyli, a dilated receptacle in the abdomen, and ascending through the thorax alongside the aorta, before curving left, and draining into the left subclavian jugular junction. In a day, it returns approximately 2 liters of lymph to the venous circulation. The right lymphatic duct, considerably shorter and more variable in its anatomy, collects from the right thorax, the right arm, and the right side of the head and neck, draining into the right subclavian jugular junction. The lymph these ducts carry is not simply the water that filtered out of the capillaries. It also contains the fat absorbed from the gut in the form of chylomicrons that enter the intestinal lymphatics, the lacteals, rather than the portal blood. This is why the thoracic duct's lymph is milky white after a fatty meal, the fat-laden chylomicrons giving it the appearance of dilute cream. The fat-soluble vitamins A, D, E, and K are absorbed via this lymphatic route alongside the dietary fat. It is also through the thoracic duct that the immune cells that have been surveying the peripheral tissues return to the blood. The lymphocytes that exit the blood in post-capillary venules travel through the lymph nodes and re-enter the circulation via the thoracic duct, maintain the constant recirculation of the adaptive immune system. The velocity of blood flow varies enormously between different segments of the vascular system, reaching approximately 40 centimeters per second in the aorta and falling to approximately 1 millimeter per second in the capillaries, a velocity difference that reflects the inverse relationship between total cross-sectional area and flow velocity, and that is precisely calibrated to allow adequate time for exchange in the capillaries. The physics of blood flow through the vascular system reflects a simple conservation principle. The total volumetric flow rate, liters per minute, must be the same at every cross-section of the circulation because blood neither accumulates nor disappears. If the flow rate is constant at 5 liters per minute, the velocity at any cross-section is the flow rate divided by the total cross-sectional area at that point. The aorta, with a single tube, approximately 2 to 3 centimeters in diameter, has a cross-sectional area of approximately 3 to 7 square centimeters, so the blood flows through it at about 40 centimeters per second. As the aorta branches into the major arteries, and then the arterioles, the number of vessels increases, but each vessel is much smaller, and the total cross-sectional area of all the arterioles together is considerably larger than that of the aorta. The velocity in the arterioles falls to approximately 1 to 5 centimeters per second. At the capillary level, the total cross-sectional area of the many millions of capillaries is approximately 2,000 square centimeters, roughly 2,000 times the area of the aorta, so the capillary velocity is approximately 1 millimeter per second. This is approximately the same as the diffusion velocity of small molecules, like oxygen and carbon dioxide, across the capillary wall. A red blood cell spends approximately 1 second in a capillary, long enough for the oxygen it carries to diffuse out and the carbon dioxide to diffuse in. The velocity profile of the circulation is not arbitrary, but is calibrated to the physiological requirements of the system, fast where speed is needed, slow where exchange is needed. The renin-angiotensin-aldosterone system, whose components have already been discussed in the context of the endocrine system, is the cardiovascular system's primary long-term regulator of blood pressure and blood volume, operating through the kidney to adjust sodium retention and vascular resistance on a timescale of minutes to days. From the cardiovascular perspective, the renin-angiotensin-aldosterone system is the bridge between the heart and kidneys, the mechanism by which the volume status of the circulation is continuously adjusted through the control of renal sodium handling. The juxtaglomerular cells of the kidney are, in effect, baroreceptors embedded in the renal afferent arterioles. They sense the perfusion pressure of the kidney and respond to a fall by releasing renin. Renin is produced in response to 3 signals: reduced renal perfusion pressure, detected by the stretch receptors of the afferent arteriole, reduced sodium chloride delivery to the macula densa of the distal tubule, and sympathetic nerve stimulation via beta-1 adrenergic receptors on the juxtaglomerular cells. The renin-angiotensin cascade, renin-cleaving angiotensinogen to angiotensin I, angiotensin-converting enzyme in the pulmonary circulation, converting angiotensin I to the active angiotensin II, produces a molecule that acts in at least 4 ways to restore blood pressure and volume: direct arteriolar vasoconstriction, stimulation of aldosterone secretion from the adrenal cortex, direct tubular sodium reabsorption in the proximal tubule, and stimulation of ADH secretion and thirst. The systemic vasodilating drugs, the ACE inhibitors, and angiotensin receptor blockers that are among the most prescribed cardiovascular medications work by interrupting this axis at its key steps, reducing the vasoconstriction and sodium retention that contribute to hypertension and the maladaptive neurohormonal activation of heart failure. The heart and the kidney are, in this system, partners in cardiovascular regulation, the heart sensing the flow implications of any change in blood volume, the kidney making the adjustments. The cardiac output distribution between the body's organs is not fixed, but is continuously adjusted to match blood flow to metabolic demand, with the brain and heart receiving priority supply, and with the gut, skin, and kidneys subject to the greatest flow reductions during exercise and sympathetic activation. At rest, the 5 liters per minute of cardiac output is distributed approximately as follows. The gut and liver receive approximately 25%, the kidneys approximately 20%, the skeletal muscle approximately 15 to 20%, the brain approximately 15%, the heart itself approximately 5%, and the remaining organs share the balance. During maximal exercise, the cardiac output rises to 25 liters per minute, and the distribution shifts dramatically. The working muscles may receive up to 80 to 85% of the total output, supported by an increase in absolute flow to the skin for thermoregulation and a maintained absolute flow to the heart. The gut, kidney, and non-working muscles receive substantially reduced absolute flows. The mechanisms governing this distribution are both local and systemic. The local metabolic vasodilation of working muscle captures an increasing fraction of the cardiac output as exercise intensifies, while sympathetic vasoconstriction reduces flow to the splanchnic and renal beds, preventing the increased cardiac output from being dissipated in the non-exercising organs. The absolute blood flow to the brain changes relatively little during exercise. Despite the large increase in cardiac output, the brain has potent autoregulatory mechanisms that maintain its perfusion across wide ranges of systemic pressure and flow. The heart's own blood flow rises substantially during exercise, driven by the metabolic vasodilation of the coronary arterioles, responding to the increased metabolic activity of the harder working myocardium. The collateral circulation, the development of alternative routes of blood supply when a primary vessel is progressively obstructed, is the cardiovascular system's angiogenic response to chronic ischemia, and is the reason that slowly progressing coronary artery disease is sometimes better tolerated than sudden total occlusion of the same vessel. When a coronary artery is gradually narrowed by atherosclerosis over years, the downstream territory that is progressively underperfused releases angiogenic signals, primarily VEGF, but also FGF and other growth factors that stimulate the growth of collateral vessels, alternative routes of blood supply that bypass the obstructed segment. These collaterals develop from pre-existing small intercoronary anastomosis, connections between branches of adjacent coronary arteries that enlarge and remodel in response to the increased pressure gradient across them created by the upstream obstruction. Well-developed collaterals can maintain sufficient blood flow to prevent resting ischemia, even when the main coronary artery is severely obstructed or completely occluded. This is why patients with slowly progressive coronary artery disease sometimes survive complete coronary artery occlusion with a relatively small infarct. The collateral supply has developed sufficiently to protect much of the territory. In contrast, the sudden, complete occlusion of a previously normal or mildly diseased artery, as in the acute thrombosis that follows plaque rupture, finds no collateral supply in place, and the entire territory is acutely ischemic. Collateral development is both a natural protection and a therapeutic target. Interventions that promote angiogenesis in ischemic myocardium by enhancing VEGF expression, by promoting physical training that increases the metabolic signal for collateral growth, have been investigated as approaches to improving collateral perfusion in patients with inoperable coronary artery disease. The concept of cardiac preconditioning, the phenomenon in which brief episodes of ischemia and reperfusion make the myocardium more resistant to a subsequent prolonged ischemic insult, is one of the most striking examples of adaptive cellular protection in biology, and has guided the development of clinical strategies to protect the heart during cardiac surgery and myocardial infarction. Ischemic preconditioning was discovered in 1986 by Charles Murray and colleagues, who showed that 4 brief cycles of coronary occlusion and reperfusion in dogs dramatically reduced the infarct size produced by a subsequent prolonged coronary occlusion, reducing infarct size by approximately 75%. The protection lasted for approximately 2 hours after the preconditioning stimulus, the classical window. A second window of protection emerges 24 to 72 hours later and may last for several days. The late preconditioning or second window of protection, mediated by transcriptional changes, rather than the acute signaling of the classical window. The molecular mechanism of ischemic preconditioning involves the activation of several parallel signaling cascades by the metabolic signals of the brief ischemic episodes: adenosine, bradykinin, opioids, and reactive oxygen species that converge on the mitochondrial ATP-sensitive potassium channel and on the mitochondrial permeability transition pore as the final effectors of protection. The protection is not confined to the heart. Preconditioning of one organ can protect another, as long as the protective signals reach the circulation. Remote ischemic preconditioning, in which brief cuff-induced ischemia and reperfusion of an arm or leg protects the heart from surgical ischemia, is mediated by humoral and neural signals from the conditioned limb. Remote ischemic preconditioning with a blood pressure cuff is now used in some cardiac surgery programs as a simple, non-invasive way to condition the heart before the ischemia of cardiopulmonary bypass. The ventricular ejection fraction, the fraction of end diastolic volume ejected with each beat, normally approximately 55 to 75%, is the most widely used clinical measure of left ventricular systolic function, and its reduction below 40% defines systolic heart failure and carries significant prognostic implications. The ejection fraction is the most commonly encountered number in cardiology, the single figure that most concisely summarizes the heart's pumping function, and that most strongly predicts outcomes in heart failure after myocardial infarction and before surgical procedures. It is calculated simply as the stroke volume divided by the end diastolic volume, the fraction of the filling volume that is actually ejected. In a normal heart, the end diastolic volume is approximately 120 to 150 milliliters, and the stroke volume is approximately 70 to 90 milliliters, giving an ejection fraction of approximately 55 to 70%. This means that the normal heart does not empty completely with each beat. Approximately 30 to 45% of its end diastolic volume remains as the end systolic volume. This residual volume provides a reserve if the ejection fraction increases, as it does under sympathetic stimulation during exercise. More of this reserve is called a pawn, allowing stroke volume to increase substantially. When the ejection fraction falls below 40%, as in the dilated cardiomyopathy of end-stage heart failure, or as a consequence of multiple previous myocardial infarctions, the heart is ejecting a smaller fraction of a larger end diastolic volume, and cardiac output is maintained at rest only at the cost of high filling pressures that back up into the pulmonary veins and produce the breathlessness of heart failure. The ejection fraction's predictive power reflects the fundamental importance of systolic function. A heart that ejects less efficiently delivers less oxygen per beat and must compensate by operating at higher filling pressures, exposing the pulmonary vasculature to the elevated back pressure that produces congestion. Before we go further, come back to the body for a moment. Feel the heartbeat if you can. Not anxiously, not looking for anything wrong. Just feel it, maybe a faint pulsing in the chest, or in the fingertips, or in the neck. The rhythm you are looking for has been there since before you were born. Each beat is the cycle we have been talking about. The filling, the contraction, the two sounds, the closing of the valves. Feel it now as something ordinary, and also, if you allow it, as something extraordinary. The same heart that has been doing this for every day of your life is doing it now. Right now. Slowly. Faithfully. Resting. The great saphenous vein, the longest vein in the body, running from the dorsum of the foot to the groin, has historically been the most commonly used conduit in coronary artery bypass surgery, harvested and reversed to serve as a bypass graft around obstructed coronary segments, though internal mammary artery grafts now provide superior long-term patency. The great saphenous vein was an early and important resource in the development of coronary artery bypass surgery. In the 1960s, when René Favaloro pioneered the technique that would become one of the most performed major surgeries in medicine. The vein's accessibility, running subcutaneously along the medial thigh and calf, harvestable through a relatively simple surgical approach, and its length, sufficient to provide multiple bypass grafts from a single leg, made it the default conduit for early bypass surgery. When reversed to correct the venous valve's direction and sewn from the aorta to the coronary artery, beyond the obstruction, the saphenous vein graft restored blood flow to the ischemic myocardium with immediate and often dramatic clinical benefit. The long-term durability of saphenous vein grafts has, however, been modest at 10 years. Approximately 40 to 50% of vein grafts have occluded or significantly stenosed, limited by the development of intimal hyperplasia, and then atherosclerosis in the wall of the grafted vein, a vessel that was never designed to carry the pressurized pulsatile flow of the arterial circulation. the internal mammary arteries, harvested from the inner chest wall, while maintaining their natural blood supply, and anastomose to the coronary arteries, have proven dramatically more durable at 10 years. Over 90% of internal mammary grafts remain patent. The current standard in bypass surgery is to use the internal mammary arteries for the most important grafts, and saphenous vein or radial artery for additional vessels when needed. The concept of vascular remodeling, the structural adaptation of vessel walls to sustain changes in pressure and flow, explains how the vasculature adapts to hypertension, exercise training, and pregnancy, and how the maladaptive remodeling of hypertension contributes to the complications of that condition. Blood vessels are not static structures, but living tissues that continuously remodel their architecture in response to the hemodynamic forces acting on them. The primary signals driving vascular remodeling are the shear stress on the endothelium, proportional to flow velocity, and the circumferential wall stress, proportional to the transmural pressure. When blood flow through a vessel increases chronically, as in a limb with a large arteriovenous fistula, or in the vessels supplying training muscles, the increased shear stress on the endothelium stimulates the release of nitric oxide and other growth factors that drive outward remodeling. The vessel enlarges to restore shear stress to its set point. This flow-induced outward remodeling is the mechanism by which physical training enlarges the coronary arteries of trained athletes. The increased coronary flow of sustained exercise training drives the coronary arteries to enlarge over months, providing a larger vessel cross-section and better reserve for peak exercise demands. In hypertension, the increased pressure increases the circumferential wall stress, and the vessel wall remodels inward. The smooth muscle hypertrophies and the wall thickens, increasing the wall-to-lumen ratio and reducing the lumen diameter. This inward hypertrophic remodeling normalizes wall stress per unit area, but at the cost of increased resistance. The thickened, narrowed arterioles of chronic hypertension are one of the mechanisms by which hypertension perpetuates itself, because the remodeled vessels offer greater resistance than normal vessels at the same contractile tone. Treating hypertension with drugs may reduce the blood pressure acutely, but the structural remodeling reverses only slowly, over months to years. Cardiac arrhythmias, abnormalities of heart rate or rhythm caused by disorders of impulse formation or conduction, range from the clinically benign to the immediately life-threatening, and their mechanism is typically classified as re-entry, abnormal automaticity, or triggered activity, each with distinct electrophysiological mechanisms and therapeutic implications. The heart's electrical system generates the heartbeat through the normal mechanisms of the sinoatrial node pacemaker and the ordered propagation of the impulse through the conduction system. Arrhythmias arise when this normal sequence is disrupted by one of three mechanisms. Re-entry, the most common mechanism for sustained clinical arrhythmias, including atrial flutter, most supraventricular tachycardias, and ventricular tachycardia requires two pathways, between which the impulse can circulate. In a closed loop, the impulse travels down one pathway, finds the other has recovered from its refractory period, travels back up the other, and the cycle perpetuates. The critical ingredients are two pathways with different conduction velocities and different refractory periods, creating a situation in which the impulse can arrive at the other pathway's entrance just as it has recovered from the previous beat. Abnormal automaticity occurs when cells outside the sinoatrial node develop enhanced spontaneous depolarization, either through disease of the myocardium, electrolyte disturbances, or sympathetic stimulation, and fire at a rate that exceeds or overrides the sinoatrial node. This is the mechanism of the accelerated junctional rhythm in digoxin toxicity and of many ectopic beats. Triggered activity involves early or late after depolarizations, oscillations in the membrane potential that follow a normal action potential, and can, if they reach threshold, trigger premature additional action potentials. Early after depolarizations, promoted by conditions that prolong the action potential, hypokalemia, many drugs that block the cardiac potassium channels, are the mechanism of the potentially fatal polymorphic ventricular tachycardia of torsades de pointes. The coagulation cascade is balanced by a parallel anticoagulation system comprising antithrombin, protein C, protein S, and tissue factor pathway inhibitor that limits clot formation to the site of injury and prevents the thrombosis of normal vessels and the hereditary or acquired deficiencies of these inhibitors cause the hypercoagulable states that predispose to venous thromboembolism. The bodies need to maintain the blood in a state of readiness for coagulation while preventing spontaneous thrombosis of normal vessels requires a sophisticated system of anticoagulant mechanisms that run in parallel with the coagulation cascade, held in balance by the endothelium. Antithrombin, a serine protease inhibitor, circulates in the plasma and slowly but continuously neutralizes thrombin and factor XA and other coagulation enzymes, limiting their activity to the immediate vicinity of the injury site. Heparan sulfate proteoglycans on the surface of the endothelium dramatically accelerate antithrombin's inhibitory activity by up to 1,000-fold, so that coagulation enzymes that diffuse from the injury site onto the normal endothelium are rapidly inactivated. This is the mechanism of action of heparin, which mimics heparan sulfate and is used as an anticoagulant drug. Protein C, activated by thrombin bound to the endothelial protein thrombomodulin, inactivates factors VA and VIIA, the cofactors that dramatically amplify the coagulation cascade, limiting the rate of thrombin generation. Protein S serves as the cofactor for activated protein C. Tissue factor pathway inhibitor directly inhibits the factor VIIA tissue factor complex that initiates the extrinsic pathway. Together, These inhibitors ensure that coagulation is confined to the site of injury and self-limiting. Hereditary deficiency of protein C, protein S, antithrombin, or the presence of factor V Leiden, a mutation that makes factor VA resistant to inactivation by protein C, causes the thrombophilic states that predispose to venous thromboembolism and recurrent pulmonary embolism. The vascular endothelium's production of prostacyclin, a prostaglandin synthesized from arachidonic acid by cyclooxygenase 2 in the endothelial cell, opposes platelet aggregation and causes vasodilation, balancing the proaggregatory and vasoconstrictive thromboxane A2 produced by activated platelets, and the disruption of this balance by selective COX-2 inhibitors explains their cardiovascular toxicity. Prostacyclin and thromboxane A2 are both derived from arachidonic acid through the cyclooxygenase pathway, but have precisely opposite effects on the vasculature, creating a balance between prohemostatic and anti-hemostatic forces at the blood vessel interface. Prostacyclin, PGI2, is produced by the endothelial cell's COX-2 and acts on IP receptors on platelets to raise cyclic AMP and inhibit their activation, and on vascular smooth muscle to cause vasodilation. Thromboxane A2, TXA2, is produced by activated platelets COX-1 and acts on TP receptors to cause vasoconstriction and further platelet activation. In the normal vessel, the endothelial prostacyclin production maintains the surrounding microenvironment as antithrombotic, preventing platelet accumulation on the intact vessel wall. Low-dose aspirin exploits this balance. Aspirin irreversibly acetylates both COX-1 and COX-2, but because platelets, which lack a nucleus, cannot synthesize new COX enzyme, the aspirin effect on platelet TXA2 production lasts the lifetime of the platelet, approximately 10 days. Endothelial cells can regenerate new COX-2 within hours. At low doses, aspirin's more complete and sustained inhibition of platelet TXA2 relative to its briefer inhibition of endothelial prostacyclin produces a net antithrombotic effect, the basis of aspirin's antiplatelet therapy. Selective COX-2 inhibitors, the COXIBs, spare the platelet COX-1 while blocking endothelial COX-2, suppressing prostacyclin while leaving TXA2 production intact and shifting the balance toward prothrombotic and vasoconstrictive, which is why the COXIBs were found to increase cardiovascular risk. The systemic inflammatory response to major infection or injury, sepsis, and the systemic inflammatory response syndrome produces a characteristic cardiovascular picture of vasodilation, increased cardiac output, and reduced vascular resistance that, if uncorrected, leads to the distributive shock of septic shock, in which perfusion pressure falls despite high cardiac output. Septic shock presents a physiological paradox that illustrates the cardiovascular system's vulnerability to endothelial dysfunction. In most forms of shock, hemorrhagic, cardiogenic, the cardiac output is low and the vascular resistance is high. The heart is not pumping enough, and the blood vessels are vasoconstricting in compensation, trying to maintain blood pressure in the face of reduced flow. In distributive shock, septic shock, anaphylaxis, neurogenic shock, the cardiac output is high and the vascular resistance is low. The problem is not insufficient pump output, but maldistribution of that output. In sepsis, the massive activation of the innate immune system by bacterial products, lipopolysaccharide from gram-negative bacteria, peptidoglycan from gram-positive bacteria, produces an inflammatory cytokine storm that dysregulates endothelial function throughout the body. Nitric oxide production is dramatically upregulated by inducible nitric oxide synthase, causing profound global vasodilation. Endothelial barrier function is disrupted by inflammatory mediators, causing massive fluid leakage from the capillaries into the interstitium, the edema of sepsis, which further depletes the intravascular volume. The myocardium itself is depressed by circulating cytokines. The combination of low peripheral resistance, depleted intravascular volume, and myocardial depression reduces the perfusion pressure to the vital organs, despite a cardiac output that may be elevated. The treatment of septic shock accordingly targets multiple components: fluid resuscitation to restore intravascular volume, vasopressors to restore vascular resistance, source control to eliminate the infectious trigger, in a physiological battle played out in the hemodynamic derangements of the circulation. The mechanism of action of the major cardiovascular drug classes, statins, beta blockers, ACE inhibitors, calcium channel blockers, and antiplatelet agents, each targets a specific component of the cardiovascular pathophysiology established in preceding decades of basic science, exemplifying the direct translation of molecular biology into clinical benefit. The pharmacological management of cardiovascular disease is among the most evidence-based in all of medicine because the molecular targets of the major drug classes were established through decades of physiological research before the drugs were developed, and the drugs' clinical benefits have been tested in randomized trials involving hundreds of thousands of patients. Statins, competitive inhibitors of HMG-CoA reductase, the rate-limiting enzyme of cholesterol synthesis, reduce LDL cholesterol by approximately 30 to 50% at standard doses, and their clinical benefit in reducing cardiovascular events has been established across primary and secondary prevention in multiple large trials. Beta blockers, competitive antagonists of the beta-adrenergic receptors, reduce heart rate and myocardial oxygen demand, reduce the risk of fatal arrhythmias after myocardial infarction, and reduce the maladaptive sympathetic activation that accelerates the progression of heart failure. ACE inhibitors, inhibitors of angiotensin-converting enzyme, reduce the vasoconstriction and aldosterone-mediated sodium retention of the renin-angiotensin-aldosterone system, benefiting both hypertension and heart failure. Calcium channel blockers, antagonists of the L-type, voltage-gated calcium channels in vascular smooth muscle and in the cardiac conduction system, reduce vascular resistance by preventing smooth muscle contraction and slow the heart rate by reducing the calcium-dependent automaticity of the sinoatrial and atrioventricular nodes. Antiplatelet agents, aspirin, clopidogrel, ticagrelor, prevent the platelet aggregation that forms the initial thrombus in acute coronary syndromes. Each of these drug classes emerged from a specific molecular understanding of cardiovascular physiology. The cardiac cycle's mechanical events can be displayed as a pressure-volume loop, a graphical representation of ventricular pressure against volume throughout the cycle, whose shape encodes the ejection fraction, the contractility, the preload, and the afterload of the ventricle, and whose alteration in disease states provides diagnostic information about the nature and severity of ventricular dysfunction. The pressure-volume loop is one of the most information-dense graphical representations in cardiovascular physiology, a single curve that traces the ventricle's behavior through an entire cardiac cycle and encodes, in its geometry, almost every relevant mechanical property of the ventricle. The loop begins at the lower right point, end diastole, where the ventricle is filled and about to contract. Systole proceeds up the right limb of the loop as pressure rises isovolumetrically, then along the upper limb as the aortic valve opens and blood is ejected at declining volume, and back to the lower left point, end systole, where ejection ceases and the aortic valve closes. Diastole proceeds down the left limb as pressure falls isovolumetrically, then along the bottom limb as the mitral valve opens and the ventricle fills, returning to end diastole. The width of the loop at any level is the stroke volume. The area enclosed by the loop is the stroke work, the mechanical work done per beat. The slope of the end systolic pressure-volume relationship, the line connecting the upper left corners of multiple loops generated at different afterloads, is the end systolic elastance, a load-independent measure of contractility. A loop shifted right along the volume axis, larger end diastolic volume, reflects increased preload. A loop shifted upward, higher peak pressure at the same volume, reflects increased afterload or improved contractility. In heart failure, with reduced ejection fraction, the loop is wide and flat, large volumes, low pressures, small stroke volume. In hypertensive heart disease, the loop is narrow and tall, small volume, high pressure, preserved stroke volume, at the cost of high wall stress. The Starling equilibrium, the balance between hydrostatic and oncotic forces across the capillary wall, that determines net fluid filtration, predicts that the net fluid filtration from the capillaries is approximately 2 to 4 liters per day under normal conditions, with lymphatic drainage returning this fluid to the circulation, and that its disruption leads to edema. Ernest Starling described, in 1896, the 4 forces governing transcapillary fluid exchange, a conceptual framework that has guided the understanding of edema for over a century and continues to inform the management of conditions ranging from pulmonary edema to nephrotic syndrome to liver failure. The capillary hydrostatic pressure, the blood pressure within the capillary, pushes fluid out through the capillary wall. The interstitial fluid hydrostatic pressure, typically near zero or slightly negative in most tissues, provides a small outward force. The plasma oncotic pressure, the osmotic force generated by the plasma proteins, primarily albumin, that cannot cross the capillary wall, pulls fluid into the capillary. The interstitial oncotic pressure, generated by the small amount of protein that has filtered into the interstitium, pulls fluid outward. The net balance of these forces, the Starling forces, in a typical capillary, is a small net outward filtration at the arterial end, driven by the higher capillary hydrostatic pressure, and a smaller net reabsorption at the venous end as the hydrostatic pressure falls. The net daily filtration is approximately 2 to 4 liters, returned to the circulation by the lymphatic system. Edema occurs when this balance is disrupted. Elevated capillary hydrostatic pressure in heart failure and venous insufficiency increases filtration. Reduced oncotic pressure in nephrotic syndrome, liver failure, and malnutrition through albumin loss or reduced synthesis reduces the reabsorptive force. Increased capillary permeability in inflammation and sepsis allows protein into the interstitium, pulling water out and reducing the oncotic gradient. Heart failure, the clinical syndrome in which the heart cannot deliver sufficient blood to meet the body's metabolic needs, or can do so only at the cost of elevated filling pressures, affects approximately 64 million people worldwide, and is characterized by a neurohumoral activation that, while initially compensatory, ultimately accelerates the deterioration of cardiac function. Heart failure is the cardiovascular system's failure mode, the state reached when the heart can no longer maintain adequate output at normal filling pressures, and the body's compensatory responses, while transiently helpful, ultimately consume the cardiac reserve they are trying to protect. The primary compensatory mechanisms are the activation of the sympathetic nervous system, which increases heart rate and contractility in the short term, but over time, desensitizes the beta-adrenergic receptors of the failing heart, causes direct cardiomyocyte toxicity from excess noradrenaline, and promotes the maladaptive hypertrophy and fibrosis that further stiffen the already failing ventricle. The activation of the renin-angiotensin-aldosterone system causes sodium and water retention that increases preload, initially beneficial under the Frank-Starling mechanism, But as filling pressures rise further, fluid accumulates in the pulmonary veins and the lung interstitium, producing the dyspnea. That is the cardinal symptom of left heart failure. The peripheral vasoconstriction of the sympathetic and RAS responses maintains blood pressure but increases afterload, the pressure against which the already failing ventricle must contract, further reducing stroke volume. The cycle is progressive. Initial pump failure activates compensatory responses, which temporarily maintain output, but over weeks to months, damage the myocardium further and increase the hemodynamic burden, driving the ventricle toward further decompensation. The pharmacological pillars of modern heart failure treatment: beta blockers, ACE inhibitors, angiotensin receptor neprilysin inhibitors, mineralocorticoid receptor antagonists, and SGLT2 inhibitors. Each address a specific arm of this maladaptive neurohumoral activation, and their combination has transformed the prognosis of heart failure. The resting heart rate, the number of beats per minute when the body is at complete rest, is inversely associated with cardiovascular mortality. In large epidemiological studies, with each 10 beat per minute increase in resting heart rate associated with approximately 10 to 20% higher mortality, and the bradycardia of the trained athlete's heart, reflecting genuine physiological benefit. The inverse relationship between resting heart rate and longevity is one of the more consistent findings in cardiovascular epidemiology, observed across multiple large cohorts in both sexes, independent of other cardiovascular risk factors. The biological rationale for this association is straightforward. A lower resting heart rate means each beat is more efficient, filling time is longer, allowing better coronary perfusion. Myocardial oxygen demand is lower at any given cardiac output, and the heart sustains less mechanical stress per day. A person with a resting heart rate of 50 beats per minute makes approximately 26 million fewer heartbeats per year than someone with a resting rate of 100, a difference in mechanical work that, compounded over decades, has real consequences for the structural integrity of the myocardium and the coronary vasculature. The bradycardia of the endurance-trained heart is a genuine physiological benefit rather than a compensation for cardiac disease. The trained heart achieves a lower resting rate through a combination of increased vagal tone, the parasympathetic system exerting a greater slowing effect on the sinoatrial node, and structural changes that allow greater stroke volume, maintaining cardiac output at the lower rate. The resting heart rate of elite endurance athletes can fall below 40 beats per minute, a value that would be pathological in an untrained individual, but in the context of training, represents a heart of exceptional efficiency. The heart is slowing toward its most favorable operating condition right now, as you lie here, as the parasympathetic system gently reasserts the tone that the day's activity had moderated. The venous valves, thin, bicuspid valves at regular intervals along the deep and superficial veins of the limbs, prevent the backflow of blood and are essential for the efficient return of blood to the heart against gravity in the upright human, and their failure produces the venous hypertension, varicosities, and eventual skin changes of chronic venous insufficiency. The veins of the lower extremities face a challenge that the arteries do not: the return of blood from the feet to the heart against the hydrostatic column of approximately 130 centimeters of blood in the upright posture. The arterial pressure that drives blood into the lower limb arteries is more than sufficient to overcome this hydrostatic head. The blood arrives at the foot arterioles at a pressure of perhaps 200 millimeters of mercury in the upright person, accounting for the gravitational component. But the venous pressure at the foot in a standing person, reflecting the full hydrostatic column, is approximately 100 millimeters of mercury. Without valves, this pressure would simply prevent venous return and produce pooling. The venous valves break the continuous column of blood into segments. Each valve holds the weight of the blood column above its segment, while the blood below the valve is propelled upward by the muscular pump of the calf. Each contraction of the calf muscles squeezes the deep veins between the muscle compartments, driving blood upward past the next valve. When the muscles relax, the valves hold the blood in place, while the veins refill with blood, propelled upward from below. This sequential valve and pump system reduces the venous pressure at the foot during walking to approximately 25 millimeters of mercury, a reduction of 75 millimeters, and is the primary mechanism of venous return from the lower limbs. Primary incompetence of the venous valves, allowing blood to reflux downward with each step, maintains the full hydrostatic pressure in the superficial veins, eventually causing the tortuous dilatation of varicose veins and the chronic skin changes of venous stasis. The concept of autoregulation, the ability of certain vascular beds to maintain constant blood flow across a wide range of perfusion pressures by adjusting their vascular resistance, protects the brain, the kidney, and the coronary circulation from the hemodynamic consequences of systemic blood pressure fluctuations. Autoregulation is the local vasculature's answer to the fundamental problem of perfusion pressure variability. Systemic arterial pressure varies continuously with posture, exercise, emotional state, and many other factors, and without local compensation, tissue blood flow would vary proportionally, dangerously so in organs like the brain and kidney, whose function is highly sensitive to perfusion. Autoregulation solves this problem by adjusting local vascular resistance to maintain constant flow across a range of perfusion pressures. In the cerebral circulation, autoregulation maintains constant cerebral blood flow across mean arterial pressures from approximately 50 to 160 millimeters of mercury. Below 50, the vessels are maximally dilated and flow falls. Above 160, the vessels are forcibly distended by the pressure. The autoregulatory mechanism is overwhelmed, and the high pressure enters the capillaries, causing the cerebral edema of hypertensive encephalopathy. The mechanisms of autoregulation include the myogenic response, the intrinsic tendency of vascular smooth muscle to contract in response to increased intraluminal pressure, and metabolic autoregulation, in which the metabolic byproducts of ischemia, when pressure falls, cause vasodilation that restores flow. In the kidney, the autoregulation of glomerular filtration rate through the juxtaglomerular apparatus's regulation of afferent arteriolar tone protects the kidney from the hydraulic damage of high pressures and maintains filtration despite blood pressure variability. In the coronary circulation, autoregulation allows the coronary arterioles to maintain constant myocardial perfusion despite the large cyclic variations in coronary perfusion pressure during systole. The myocardium has the highest resting oxygen extraction of any organ in the body, extracting approximately 70% of the oxygen delivered to it by the coronary blood, compared to approximately 25% for the body as a whole, which means that the heart cannot significantly increase oxygen extraction during increased demand, and must instead depend entirely on increased coronary blood flow. Most tissues of the body maintain a substantial oxygen extraction reserve. At rest, approximately 25% of the delivered oxygen is extracted, leaving 75% in the venous blood as a buffer that can be called upon when oxygen demand increases. During exercise, skeletal muscle can increase its oxygen extraction from approximately 25 to 85%, a 3.5-fold increase in extraction that supplements the increase in blood flow in meeting the increased oxygen demand. The heart has no such reserve. Even at rest, it extracts approximately 70% of the oxygen in the coronary blood. Its venous oxygen saturation is approximately 30% compared to the systemic venous saturation of approximately 75%. At maximal exercise, extraction can rise to approximately 90%, but this represents only a 30% increase, modest compared to the 5 to 7-fold increase in cardiac oxygen demand that maximal exercise produces. The heart's solution to this constraint is to depend almost entirely on increased coronary blood flow rather than increased oxygen extraction to meet increased demands. Coronary blood flow, approximately 250 milliliters per minute at rest, must rise to approximately 1 liter per minute or more during maximal exercise, a 4-fold increase provided by coronary arteriolar vasodilation driven by metabolic signals from the working myocardium. Any limitation on this flow by coronary artery disease narrowing the vessels by loss of the vasodilatory capacity produces myocardial ischemia during exercise. The heart's extreme dependence on coronary blood flow amplification is why coronary artery disease produces its most dramatic consequences, angina and infarction, during demand. The electrocardiographic QT interval The time from the onset of ventricular depolarization to the end of ventricular repolarization is prolonged by hypokalemia, hypomagnesemia, and many drugs, including some antiarrhythmics, antibiotics, and antipsychotics, and a prolonged QT interval predisposes to the potentially fatal polymorphic ventricular tachycardia, known as torsades de pointes. The QT interval is one of the most clinically surveilled measurements on the electrocardiogram, precisely because its prolongation is both common, caused by dozens of drugs, several electrolyte disturbances, and several hereditary channelopathies, and potentially lethal. The interval reflects the duration of the ventricular action potential, and its prolongation reflects a delay in the repolarization that ends the action potential. The primary repolarizing current in ventricular cardiomyocytes is the rapidly activating delayed rectifier potassium current, IKR, encoded by the HERG gene. This current is the target of most drugs that cause QT prolongation. They block the HERG channel, reducing the repolarizing potassium current and prolonging the action potential. Hypokalemia does the same by a different mechanism. Low extracellular potassium increases the voltage driving potassium out of the cell, reducing the driving force for IKR, and thereby reducing the rate of repolarization. The prolonged action potential creates the conditions for early after depolarizations, abnormal depolarizations occurring during the repolarization plateau, which, if they reach threshold, trigger premature ventricular beats. When these premature beats strike during the vulnerable window of repolarization of the preceding beat, the RNT phenomenon, they can initiate torsades de pointes, a rapid, twisting polymorphic ventricular tachycardia that typically terminates spontaneously in 20 to 60 seconds, but can degenerate into ventricular fibrillation. The management of QT prolongation involves removing the offending drug, correcting electrolyte disturbances, and in congenital long QT syndrome, implanting a defibrillator or prescribing beta blockers to reduce the sympathetic triggers for torsades. The lymphatic endothelium differs from the vascular endothelium in expressing specific molecular markers, including LYVE1, PROX1, and PDPN, and in forming the button-like junctions, rather than the zipper junctions, of blood capillaries that allow tissue fluid and cells to enter the lymphatic capillaries while preventing backflow. The lymphatic capillaries architecture reflects its fundamentally different function from the blood capillary. The blood capillary is a selective filter. It must allow the controlled passage of small molecules while retaining cells and proteins. The lymphatic capillary is a collector. It must allow the free entry of proteins, cells, lipid particles, and tissue fluid. This difference in function is reflected in two structural differences. First, lymphatic capillary endothelial cells are connected by button-like junctions, discontinuous attachments at intervals along the cell borders, rather than the continuous zipper-like junctions of blood capillaries. These button junctions form flap-like openings that can open passively in response to increased interstitial pressure, allowing fluid and cells to enter and close when the pressure in the lymphatic lumen exceeds that in the interstitium, preventing backflow. Second, the lymphatic capillaries lack a continuous basement membrane and the parasite coverage of blood capillaries. They are anchored instead to the surrounding extracellular matrix by fine collagen filaments that hold the vessel open when interstitial pressure rises and tissue swells. When edema develops, when interstitial fluid accumulates, the tension on these anchoring filaments pulls the lymphatic capillary open, increasing its collecting capacity at precisely the moment it is most needed. The lymphatic capillary is, in this sense, a passive valve that opens in response to the problem it must solve. The phenomenon of flow-mediated dilation, the endothelium-dependent vasodilation that occurs when blood flow through an artery is temporarily increased after a period of occlusion, is used clinically and in research as a non-invasive measure of endothelial function, and its impairment is an early marker of cardiovascular disease risk. Flow-mediated dilation is the in vivo expression of the shear stress nitric oxide vasodilation axis of endothelial function, the mechanism by which the endothelium detects increased blood flow and responds by releasing nitric oxide to dilate the vessel, reducing resistance and maintaining the shear stress at its physiological set point. In the clinical test, a cuff is inflated around the upper arm to occlude brachial artery flow for 5 minutes. When the cuff is released, the accumulated vasodilatory metabolites cause a brief, reactive hyperemia, a large increase in forearm blood flow that markedly increases the shear stress on the brachial artery endothelium. In a person with healthy endothelial function, this shear stress stimulates robust nitric oxide production, and the brachial artery dilates by approximately 10 to 15% within 60 seconds, detectable by ultrasound. In a person with impaired endothelial function, as in the presence of cardiovascular risk factors, including hypertension, diabetes, hypercholesterolemia, and smoking, the nitric oxide production is blunted and the dilation is less. Flow-mediated dilation has been shown in multiple studies to predict future cardiovascular events independently of traditional risk factors, making it a window into the preclinical vascular dysfunction that precedes clinical disease. Interventions that improve endothelial function, regular exercise, statin therapy, blood pressure treatment, smoking cessation, improve flow-mediated dilation, and this improvement correlates with reductions in cardiovascular event rates. The cardiac biomarkers, troponin INT, released from damaged cardiomyocytes into the circulation within hours of myocardial injury, have transformed the diagnosis and risk stratification of acute coronary syndromes, by providing a highly sensitive and specific blood test for myocardial damage that can quantify the degree of injury and guide treatment decisions. The measurement of troponin in blood as a marker of myocardial injury is one of the most consequential advances in cardiac diagnostics of the past 30 years. Troponin I and troponin T, the cardiac-specific isoforms of the regulatory proteins of the thin filament, are present in cardiomyocytes in very high concentrations and are almost entirely absent from non-cardiac tissue and health. When cardiomyocytes are irreversibly injured by ischemia, by myocarditis, by trauma, by certain drugs, their cell membranes lose integrity, and the intracellular contents, including the cytoplasmic pool of free troponin, are released into the interstitium and then into the blood. The rise in blood troponin begins within 2 to 4 hours of myocardial injury, peaks at 12 to 24 hours, and returns to baseline over 5 to 14 days. The introduction of high-sensitivity troponin assays, capable of detecting troponin concentrations at the femtomolar level, has dramatically lowered the detection threshold, allowing myocardial injury to be detected from blood samples taken 1 to 3 hours after the onset of symptoms, rather than the 6 to 12 hours previously required. The high sensitivity has also revealed that myocardial injury is not confined to acute myocardial infarction, but occurs in many conditions, including heart failure, pulmonary embolism, myocarditis, renal failure, and severe sepsis, a finding that has expanded the clinical utility of troponin measurement beyond the coronary care unit to the general medical population. The absolute troponin level, the pattern of rise and fall over serial measurements, and the clinical context together determine whether the injury represents acute coronary syndrome or a non-ischemic cause. The blood type system, the ABO and rhesus classification of red cell surface antigens, is clinically critical for blood transfusion compatibility because the immune system generates antibodies against the absent ABO antigens from early life, and transfusion of incompatible blood triggers a hemolytic transfusion reaction that can be rapidly fatal. The ABO blood group system is based on the expression of 2 carbohydrate antigens, antigen A and antigen B, on the surface of red blood cells. The expression of neither group O, either one, groups A or B, or both, group AB, determined by the alleles of the ABO gene, inherited from each parent. What makes this system clinically treacherous is the naturally occurring antibodies. From approximately 4 to 6 months of age, people develop IgM antibodies against the ABO antigens they do not carry, without any prior transfusion or exposure to foreign red cells. The antibodies arise through exposure to environmental antigens on gut bacteria that share structural features with the ABO carbohydrates. Group A individuals have naturally occurring anti-B antibodies. Group B individuals have anti-A. Group O individuals have both anti-A and anti-B. Group AB individuals have neither. when incompatible blood is transfused, as when Group O blood, containing anti-A and anti-B antibodies, is given to a Group A or Group B recipient. The recipient's red cells are immediately attacked by the antibodies in the transfused plasma, or vice versa when Group A blood is given to a Group O recipient. The complement system is activated. The red cells lyse intravascularly, and the released hemoglobin precipitates in the renal tubules, causing acute renal failure. The massive complement activation and cytokine release produce shock, disseminated intravascular coagulation, and if not rapidly recognized and treated, death. The careful checking of blood type compatibility before transfusion, the cross-match, is the primary safety step that prevents this catastrophe. The coronary circulation's unique physiology, particularly the compression of the left coronary arteries during systole, and the consequent restriction of left ventricular coronary perfusion primarily to diastole, means that the diastolic blood pressure and the diastolic duration are the primary determinants of myocardial oxygen supply, explaining why the diastolic pressure and heart rate are the key targets for anti-ischemic therapy. The coronary circulation faces a mechanical challenge, unique in the body, the very contraction of the heart that drives all other organ perfusion, temporarily interrupts its own perfusion. During systole, the intramyocardial pressure in the left ventricular wall rises to equal or exceed the aortic pressure, and the left coronary arteries embedded in this wall are compressed and their perfusion is transiently reduced or reversed. In the subendocardium, the innermost layer of the left ventricular wall, under the highest compressive force, flow may actually reverse during systole. As a result, approximately 80% of left ventricular coronary perfusion occurs during diastole, when the myocardium is relaxed and the compressive force is absent. The driving pressure for this diastolic coronary flow is the diastolic blood pressure, the pressure that persists in the aorta between heartbeats, minus the pressure in the left ventricle at the end of diastole. When diastolic pressure falls, from hypotension, from aortic regurgitation, the coronary driving pressure falls, and myocardial perfusion is compromised. When the heart rate rises, diastole is shortened disproportionately. At 120 beats per minute, diastole is only approximately 250 milliseconds, compared to 500 milliseconds at 60 beats per minute. Both the absolute time available for diastolic perfusion and the diastolic pressure are reduced at high heart rates. This is why rate control, reducing the heart rate in acute coronary ischemia, is such an effective anti-ischemic measure. It simultaneously increases the diastolic duration, more time for coronary perfusion, and reduces myocardial oxygen demand. Lower rate means fewer contractions per minute. There are so many places left to go in the cardiovascular system tonight. The microcirculation, the vascular biology of exercise, the electrical abnormalities of the failing heart, the extraordinary plasticity of the vessels themselves. If you would like to be here for those journeys, and for all the other quiet wonders that Relax with Science brings to the night, one slow evening at a time, subscribing keeps the door open between us. Something will be waiting on an evening when you need it. Made slowly, made carefully, made for exactly this hour. The fibrinolytic system, the enzymatic system that dissolves fibrin clots through plasmin, is the counterbalance to the coagulation cascade and is activated simultaneously with coagulation to prevent excessive clot extension, with tissue plasminogen activator as the primary activator of plasminogen to plasmin, and with alpha-2 antiplasmin as the primary inhibitor. The fibrinolytic system is coagulation's housekeeper, the system that limits the size of clots, gradually dissolves them as healing proceeds, and maintains the patency of vessels by preventing the permanent occlusion that would result if clots persisted indefinitely. Tissue plasminogen activator, TPA, is produced by endothelial cells and released in response to thrombin, fibrin, and shear stress, precisely the conditions that accompany clot formation. TPA is catalytically inefficient in the absence of its cofactor fibrin, but becomes highly efficient when it binds to fibrin within the clot, a specificity that concentrates fibrinolytic activity within the clot rather than in the systemic circulation. TPA converts plasminogen, a circulating proenzyme, to plasmin, the active serine protease that cleaves fibrin at multiple sites, degrading the clot into fibrin degradation products. Alpha-2 antiplasmin in the plasma rapidly neutralizes any plasmin that escapes into the circulation, preventing systemic fibrinolysis. The fibrinolytic system is the basis of thrombolytic therapy. Recombinant TPA and its derivatives are administered to patients with acute myocardial infarction or ischemic stroke to dissolve the thrombus responsible and restore perfusion, achieving the same effect as mechanical reperfusion, but applicable in settings where catheterization facilities are unavailable. The therapeutic window for thrombolysis is narrow, effective if given within 3 to 4.5 hours of stroke onset, with increasing hemorrhagic risk beyond this window, and represents the attempt to pharmacologically mimic the body's own system for clearing pathological clots at a speed that the natural system cannot achieve. The concept of turbulent versus laminar blood flow and the transition between them governed by the Reynolds number explains why the heart murmurs of valvular disease and high flow states are audible, why atherosclerosis develops preferentially at arterial bifurcations and curvatures, and why the endothelium is differently activated at high and low shear stress sites. Blood flow in most of the normal vasculature is laminar, the fluid moving in concentric layers, with the fastest flow in the center and the slowest adjacent to the vessel wall, with no lateral mixing between layers. This orderly flow exposes the endothelium to a uniform, physiological level of shear stress, the frictional force of the flowing blood on the endothelial surface that stimulates the production of nitric oxide, an anti-inflammatory, antithrombotic mediators. At sites of bifurcation, curvature, or stenosis, the geometry disrupts the orderly parallel flow, boundary layer separation, flow reversal, oscillatory shear, and regions of low mean shear stress develop in the recirculation zones on the downstream side of the bifurcation. These disturbed flow regions expose the endothelium to low, oscillatory, or reversed shear stress, which suppresses enos expression and nitric oxide production, while upregulating inflammatory gene expression, adhesion molecule expression, and the oxidation of LDL, precisely the early events of atherosclerosis. The preferential development of atherosclerotic plaques at the outer wall of arterial bifurcations, at the inner curves of vessels, and at sites of post-stenotic turbulence is the direct consequence of the endothelial dysfunction caused by disturbed flow. The Reynolds number, the dimensionless ratio of inertial to viscous forces in the flow, predicts the transition from laminar to turbulent flow. Above approximately 2000 in a straight tube, flow becomes turbulent, generating the chaotic, fluctuating velocities that produce audible sounds. The heart murmurs heard through a stethoscope. The pacemaking cells of the sinoatrial node undergo spontaneous diastolic depolarization. The funny current, through ion channels that allow inward sodium and potassium flow when the membrane is hyperpolarized, gradually raising the membrane potential toward the threshold for the next action potential and determining the intrinsic firing rate of the node. The funny current, named by Dario De Francesco in 1979, for the strange inward current, activated by hyperpolarization rather than depolarization, the opposite of all other voltage-gated currents, is the molecular basis of the heart's automaticity. The HCN channels, hyperpolarization-activated, cyclic nucleotide-gated channels that carry the funny current, are activated when the membrane potential falls below approximately -60 millivolts, as it does at the end of each action potential repolarization. Once activated, these channels allow the simultaneous inward flow of sodium and potassium ions, a net inward, depolarizing current that gradually raises the membrane potential from its post-repolarization minimum of approximately -65 millivolts toward the threshold for the next action potential at approximately -40 millivolts. The rate at which the funny current drives this spontaneous diastolic depolarization, the slope of the pacemaker potential, determines the rate of spontaneous firing, and therefore the heart rate. Sympathetic stimulation increases heart rate by increasing the production of cyclic AMP in the sinoatrial node cells, which binds to the HCN channels and shifts their activation voltage, making them activate at less negative potentials and increasing the slope of the pacemaker potential. Parasympathetic stimulation does the opposite, decreasing cyclic AMP and slowing the slope. The IF current is also the target of ivabradine, a selective HCN channel blocker used to reduce heart rate in patients with heart failure and angina. without the blood pressure-lowering effects of beta blockers, a pharmacological exploitation of the funny current's role as the heart rate's molecular metronome. The role of the spleen in cardiovascular physiology extends beyond its immunological function to include its role as a blood reservoir, sequestering approximately 200 to 300 milliliters of red blood cells that can be rapidly mobilized into the circulation during exercise or hemorrhage through sympathetic-mediated splenic contraction. The spleen's cardiovascular role as a blood reservoir is more prominent in some mammals. Horses and dogs can mobilize several liters of red cell-rich blood from the spleen within minutes of exercise, producing a dramatic hematocrit rise that substantially increases their oxygen-carrying capacity. In humans, the effect is more modest, but physiologically relevant. The human spleen contains approximately 200 to 300 milliliters of blood, at higher hematocrit than the systemic circulation. The spleen's filtering function concentrates red cells in the red pulp, and this concentrated red cell pool is available for rapid mobilization. During intense exercise, sympathetic activation causes contraction of the capsule and trabecular smooth muscle of the spleen, expelling this reservoir into the circulation and increasing the circulating hematocrit by approximately 2 to 3%, a modest but real augmentation of the oxygen-carrying capacity that may contribute to the cardiovascular response to maximal exercise. During hemorrhage, splenic contraction similarly mobilizes this reserve in the autotransfusion response. The spleen also removes aged, damaged, and abnormally shaped red cells from the circulation. The red pulp macrophages, subjecting passing red cells to the mechanical challenge of squeezing through the narrow splenic sinusoids, destroying any cell that has lost the deformability required to pass. Hemolytic diseases, sickle cell disease, hereditary spherocytosis, autoimmune hemolytic anemia, are therefore accompanied by splenomegaly, as the spleen's clearance function is chronically overloaded. The blood viscosity in the microcirculation is lower than predicted from whole blood measurements because of the Farias-Lindqvist effect, the migration of red cells to the center of very small vessels, leaving a cell-poor plasma layer at the wall that effectively lubricates the flow, and the Farias effect, the reduction in hematocrit in small vessels as cells travel faster than plasma. The rheology of blood in the microcirculation defies the simple predictions of Newtonian fluid mechanics, and the discrepancies reveal the fascinating interactions between the cellular nature of blood and the geometry of the tiny vessels it must traverse. In vessels smaller than approximately 300 micrometers in diameter, red blood cells tend to migrate toward the center of the lumen, the axial migration driven by the parabolic velocity profile of laminar flow, which exerts a net force, pushing deformable particles away from the slow-moving wall toward the faster-moving center. The result is a marginal cell-free layer at the vessel wall, rich in plasma and poor in cells, that lubricates the wall-blood interface and reduces the effective viscosity of the blood in small vessels compared to large vessels. This is the Farias-Lindqvist effect, which means that the apparent viscosity of blood is lower in capillaries and arterioles than in larger vessels, a physiologically beneficial reduction that decreases the cardiac work required to perfuse the microcirculation. The Farias effect complements this because the red cells migrate to the center, where the velocity is higher. The red cells transit small vessels faster than the plasma, and the hematocrit in a small vessel segment is actually lower than in the supplying large vessel. The cells are moving through faster and spending less time in any given segment. Both effects reduce the hematocrit and effective viscosity in the microcirculation, facilitating the perfusion of the smallest vessels. Heart rate recovery, the rate at which heart rate falls after exercise ceases, is a measure of parasympathetic reactivation that has strong prognostic value, with a fall of less than 12 beats per minute in the first minute after exercise cessation, associated with significantly increased cardiovascular mortality in multiple large studies. The speed at which the heart rate returns toward its resting value after exercise is determined primarily by the speed of parasympathetic reactivation, the resumption of vagal tone to the sinoatrial node as the sympathetic activation of exercise subsides. In healthy individuals with well-trained autonomic nervous systems, the parasympathetic system reactivates rapidly upon exercise cessation, and the heart rate falls sharply in the first minute, typically by 20 beats per minute or more. In individuals with impaired autonomic function, as is seen with aging, with heart failure, with diabetes, and as a general feature of reduced cardiovascular fitness, parasympathetic reactivation is slower, and the first-minute heart rate recovery is blunted. The prognostic significance of a slow heart rate recovery was established in a landmark paper from the Cleveland Clinic in 1999, which showed that a fall of 12 beats per minute or less in the first minute after a standard treadmill exercise test was associated with a doubled risk of death over 6 years, independent of other exercise test findings and clinical risk factors. Subsequent studies have confirmed this finding across diverse populations. Heart rate recovery is, in this sense, a non-invasive window into the autonomic health of the cardiovascular system, a simple measurement that integrates the health of the sinoatrial node, the vagal effort pathways, the adrenergic state, and the overall physiological fitness of the cardiovascular regulation system into a single number. The study of the cardiovascular system's response to microgravity in astronauts, including the cephalad fluid shift, cardiac atrophy, reduced plasma volume, and orthostatic intolerance on return to Earth, has provided unique insights into the mechanisms by which gravity shapes the normal cardiovascular physiology of upright humans. Human beings evolved in gravity, and the cardiovascular system has adapted its architecture and its regulatory responses to the specific hemodynamic challenges of the upright posture in a 1G environment. The gravitational pooling of blood in the lower extremities during standing, the reason that the venous return mechanisms of valves, muscle pump, and respiratory pump are necessary, is entirely absent in microgravity. In space, approximately 1 liter of fluid shifts from the lower extremities to the head and thorax within hours of arriving in microgravity, increasing central blood volume and triggering a series of counter-regulatory responses. Diuresis reduces plasma volume by approximately 10 to 15%. The renin-angiotensin-aldosterone system is suppressed, and aldosterone and ADH are reduced. The heart, receiving chronically increased venous return to the right atrium, remodels toward a smaller, more spherical shape. Cardiac atrophy over the weeks of the mission. On return to Earth, the shrunken plasma volume, the reduced cardiac reserve, and the reset baroreflexes combine to make orthostatic hypotension a significant problem. The returning astronaut, standing for the first time in weeks or months, has insufficient cardiovascular capacity to maintain blood pressure against gravity and may faint within seconds. The cardiovascular challenges of spaceflight have driven detailed physiological studies of fluid regulation, baroreceptor function, and cardiac remodeling that have illuminated the mechanisms by which the terrestrial cardiovascular system maintains its remarkable adaptation to the upright human posture. I wonder how you are feeling right now, whether the day has released its last hold, or whether there is still some residue of it in the chest, in the shoulders, in the quality of the thoughts. Whether the heart has found its slower rhythm. If it has, even partially, I am glad. The heart rate right now, lower than it was an hour ago, is a physical sign of safety that the nervous system is reading and responding to. You are telling your own cardiovascular system that it is safe to rest. And if you feel like leaving something in the comments about what this night feels like, I would genuinely love to read it. Sometimes the most important thing is simply, I was here. The night was quiet. That was enough. The heart's ability to vary its output from 5 to 25 liters per minute, a 5-fold increase, is achieved through simultaneous increases in heart rate and stroke volume, with heart rate contributing approximately 60% of the increase, and stroke volume approximately 40%, the relative contributions depending on training status and exercise intensity. The 5-liter resting cardiac output and the 25-liter maximal output of the trained athlete represent the two endpoints of a remarkably wide operating range, and understanding how the heart moves between them illuminates the physiological machinery of exercise. At rest, the resting cardiac output is the product of a heart rate of approximately 70 beats per minute and a stroke volume of approximately 75 milliliters. At maximal exercise in an elite endurance athlete, the cardiac output is the product of a heart rate of approximately 190 beats per minute, and a stroke volume of approximately 130 to 150 milliliters, both elevated simultaneously, multiplicatively producing the enormous cardiac output. The heart rate increase is driven by the progressive withdrawal of parasympathetic tone at lower exercise intensities, and the progressive increase in sympathetic activation at higher intensities. The stroke volume increase is driven by the Frank-Starling mechanism, increased venous return from the muscular pump of exercise, increases the end diastolic volume, and by the positive inotropic effect of sympathetic stimulation, which increases the contractility of the myocardium and allows more complete ejection at the shorter diastolic filling times of high heart rates. In untrained individuals, the stroke volume increases primarily at low to moderate exercise intensities and may plateau at higher intensities as the shortened filling time limits preload. In trained athletes, the enlarged cardiac chambers and enhanced ventricular compliance allow stroke volume to continue rising at higher exercise intensities, contributing a larger fraction of the cardiac output increase. The athlete's heart is not simply a heart that beats more, it is a heart that fills more and ejects more with each beat. The microcirculation of the coronary vessels includes a phenomenon called myocardial bridging, the partial enclosure of coronary artery segments within the myocardial muscle itself, which causes systolic compression of the bridged segment and has been implicated in a spectrum of symptoms, from mild ischemia to acute coronary syndromes. Myocardial bridging occurs when a coronary artery, most commonly the left anterior descending artery, in its mid-segment, dips beneath the myocardial muscle, rather than running on the surface of the heart, in the epicardial fat. The muscle fibers overlying the buried segment form a bridge, and with each systolic contraction, these fibers compress the coronary segment they enclose, reducing its luminal diameter by 60 to 90%. This systolic compression is, in isolation, perhaps less alarming than it sounds. As already noted, most left ventricular coronary perfusion occurs in diastole, and the systolic compression of a bridged segment reduces flow primarily in systole, when flow would be limited anyway. In many people, myocardial bridging is an incidental finding without clinical significance. But in others, particularly when the bridge is long and deep, when there is underlying coronary disease, or when conditions such as tachycardia shorten the diastolic perfusion time, the bridged segment's systolic compression may produce significant ischemia. There is also evidence that the altered flow dynamics in the region just proximal to the bridge, where disturbed oscillatory flow develops during the compression relaxation cycle, create an environment predisposed to the development of atherosclerosis, even though the bridged segment itself is characteristically free of atheroma. The study of myocardial bridging has contributed to the understanding of how hemodynamic forces shape the distribution of coronary atherosclerosis. The blood clotting time, the duration between the initiation of coagulation and the formation of a visible clot, is measured clinically by the prothrombin time and the activated partial thromboplastin time, which assess the extrinsic and intrinsic pathways respectively, and their prolongation by anticoagulant drugs or factor deficiency guides both diagnosis and therapy. The prothrombin time, the time required for plasma to clot when tissue factor is added, tests the extrinsic pathway and the common pathway, factor 7, X, V, prothrombin, and fibrinogen. Expressed as the international normalized ratio relative to a standardized control, the PT/INR is the primary laboratory test used to monitor the intensity of warfarin anticoagulation. Warfarin acts by inhibiting the vitamin K-dependent carboxylation of factors 2, prothrombin, 7, 9, and X, reducing the activity of all four simultaneously. The PT/INR, sensitive primarily to factor 7, the extrinsic pathway factor with the shortest half-life, rises as these factors are depleted. The target INR of 2 to 3, for most indications, atrial fibrillation, venous thromboembolism, reflects the therapeutic window in which the risk of thrombosis is substantially reduced and the risk of major bleeding is acceptably low. The activated partial thromboplastin time, the clotting time with a contact activator, phospholipid, and calcium added, tests the intrinsic pathway and the common pathway, factors 12, 11, 9, 8, X, V, prothrombin, and fibrinogen. The APTT is the primary test for monitoring unfractionated heparin anticoagulation, and its prolongation in the absence of anticoagulant therapy suggests a deficiency of an intrinsic pathway factor, most importantly factor 8 in hemophilia A, or factor 9 in hemophilia B. The two tests together provide a reasonably complete picture of the coagulation system's status and guide both the diagnosis of bleeding disorders and the dosing of anticoagulant therapy. The generation of coronary artery disease risk from classical risk factors, hypertension, hypercholesterolemia, diabetes, smoking, and family history, is not simply additive, but multiplicative in some models, reflecting the synergistic interaction of these factors on endothelial function, lipid oxidation, inflammatory signaling, and plaque vulnerability. The Framingham Heart Study, the longitudinal cohort study of a Massachusetts town that began in 1948 and has now extended into its third generation of participants, established the concept of the cardiovascular risk factor, identifying through careful epidemiological observation the factors associated with future coronary artery disease. The major modifiable risk factors: hypertension, elevated LDL cholesterol, diabetes mellitus, cigarette smoking, and physical inactivity, each independently increase cardiovascular risk, and they interact in ways that are roughly multiplicative rather than additive. A person with 3 risk factors does not have a risk. That is simply the sum of the 3 individual risks. The risk is substantially higher because the factors interact biologically. Hypertension and oxidized LDL together damage the endothelium more than either alone. Diabetes and hypercholesterolemia together accelerate macrophage foam cell formation more than either alone. Smoking and hypertension together promote plaque instability more than either in isolation. The SCORE and Framingham risk score tools that estimate 10-year cardiovascular risk from combinations of risk factors reflect this multiplicative interaction in their mathematical models. The multiplicative relationship between risk factors also explains the dramatic risk reduction that can be achieved by addressing multiple risk factors simultaneously. A statin for cholesterol and an ACE inhibitor for blood pressure and smoking cessation together reduce cardiovascular risk by substantially more than the individual contributions would suggest, because each intervention reduces the synergistic amplification of the others. The phenomenon of ischemic cardiomyopathy, the heart failure that develops from repeated myocardial infarctions, chronic ischemia, or both, illustrates how the cardiovascular system's limited capacity for cardiomyocyte regeneration means that even small losses of myocardium are permanent and cumulative, eventually leading to the ventricle's structural and functional failure. Adult human cardiomyocytes have a very limited capacity for regeneration, approximately 0.5% per year, declining with age, which means that the approximately 1 billion cardiomyocytes of the adult ventricle are largely the same cells throughout adult life, with only modest turnover. When myocardial infarction destroys cardiomyocytes, and each infarction may destroy tens to hundreds of millions, those cells are replaced, not with new cardiomyocytes, but with fibrotic scar tissue that cannot contract. The surviving cardiomyocytes hypertrophy to compensate for the lost contractile mass, and the ventricle undergoes the progressive dilatation and geometric remodeling of post-infarction remodeling, becoming rounder, larger, and less efficient as the muscle-to-scar ratio falls. Serial infarctions, or the diffuse fibrosis of chronic ischemia without frank infarction, progressively deplete the functional myocardial mass until the ventricle cannot maintain adequate output without the elevated filling pressures that produce symptoms of heart failure. The irreversibility of cardiomyocyte loss and the consequent permanence of each infarction's contribution to the heart failure trajectory is why the prevention of myocardial infarction is so much more effective than the treatment of its consequences. Research into cardiac regeneration through stem cell therapy, through the activation of the residual cardiomyocyte proliferative capacity, through tissue engineering, represents an attempt to overcome this fundamental limitation of the cardiac repair response. The concept of vascular stiffness, the reduced compliance of the large arteries that occurs with aging, hypertension, and diabetes, produces the widened pulse pressure of isolated systolic hypertension in the elderly, and is increasingly recognized as an independent cardiovascular risk factor. Beyond the blood pressure, it contributes to generating arterial stiffness, measured by the pulse wave velocity, the speed at which the pressure wave generated by each heartbeat travels along the aorta, increases progressively with age, reflecting the structural changes in the aortic wall, the progressive cross-linking and calcification of elastin fibers, the increase in the collagen to elastin ratio, and the smooth muscle hypertrophy and fibrosis of chronic hypertension. In young adults, the pulse wave velocity in the aorta is approximately 4 to 6 meters per second. By the 7th and 8th decades, it may exceed 10 to 12 meters per second, a speed at which the reflected pulse wave returns to the heart during systole rather than diastole, adding to the systolic burden rather than diastolic perfusion pressure. This early wave reflection is one of the mechanisms by which arterial stiffness increases systolic blood pressure, while diastolic pressure may fall or remain stable. The pattern of isolated systolic hypertension that characterizes arterial aging. The increased systolic pressure increases left ventricular afterload, driving concentric hypertrophy. The reduced diastolic pressure reduces the coronary perfusion gradient. Both consequences increase the risk of adverse cardiac events. Pulse wave velocity is now used in clinical research and increasingly in clinical practice as an independent measure of vascular aging, capturing the cardiovascular risk attributable to arterial stiffness that is not fully reflected in the blood pressure alone. The electrocardiographic P wave, the first deflection of each cardiac cycle, representing atrial depolarization, is absent in atrial fibrillation, replaced by the rapid, chaotic fibrillatory activity of 300 to 600 irregular atrial activations per minute, of which only a fraction conduct through the AV node to produce the irregular ventricular response. That is the ECG hallmark of this most common sustained arrhythmia. Atrial fibrillation, affecting approximately 40 million people worldwide, with prevalence rising steeply with age, from less than 1% under 65 to approximately 10% over 80, is the arrhythmia whose consequences dominate the landscape of cardiac rhythm management. In atrial fibrillation, the normal sinoatrial node-driven atrial activation is replaced by multiple simultaneous reentrant wavelets circulating through the atrial myocardium in a chaotic, self-perpetuating pattern. The AV node, bombarded by these multiple rapid and irregular activation wavefronts, conducts a variable and unpredictable fraction of them to the ventricles, typically allowing 100 to 160 ventricular activations per minute at the onset of untreated atrial fibrillation, producing the rapid and irregular ventricular rate. That is the clinical hallmark. The irregular ventricular response produces the variable stroke volumes that result from the variable diastolic filling times, shorter filling times producing smaller strokes, longer producing larger, and the irregular pulse, and symptoms of palpitation. The clinical consequences of atrial fibrillation extend beyond the arrhythmia itself. The loss of organized atrial contraction reduces the atrial contribution to ventricular filling, the atrial kick, by 15 to 20%, which can significantly impair the cardiac output in patients with already compromised ventricular filling, as in hypertrophic cardiomyopathy or critical aortic stenosis. And most seriously, the stagnant blood in the left atrial appendage, the small, finger-like outpouching of the left atrium, whose trabeculated interior is ideally designed for clot formation during fibrillation, can form thrombi that embolize to the cerebral circulation, producing the cardioembolic strokes that account for 30% of all ischemic strokes, and that make anticoagulation the most important long-term treatment in atrial fibrillation. The Wynn-Kessel effect of the elastic aorta, which dampens the pulsatile cardiac output into a more continuous peripheral flow, is progressively lost as the aorta stiffens with age, and the physiological consequence of this loss, the transmission of a more pulsatile flow to the peripheral organs, contributes to the microvascular damage of the brain, kidneys, and retina, seen in hypertension and aging. The pulsatility of flow in the large arteries is physiologically normal and managed by the Wynn-Kessel buffering of the aorta. But in the microcirculation of low-resistance organs, the brain, the kidney, and the retina, excessive pulsatility is damaging. The microvascular beds of these organs are designed for continuous, low pulsatility flow. Their autoregulatory arterioles protect the capillaries from the large pressure swings of the arterial pulse. When the aortic Wynn-Kessel is functioning normally, the arterioles of these organs receive a flow that has been substantially smoothed by aortic compliance, and their autoregulatory task is manageable. When the aorta stiffens, with age, with hypertension, the pulsatility of the aortic pressure wave is transmitted further into the arterial tree, reaching the small arteries and arterioles of the low-resistance organs at a higher amplitude than normal. The arterioles may not be able to fully attenuate this excessive pulsatility, and the capillaries are exposed to higher than normal pulsatile pressures that cause mechanical stress on the capillary walls. In the cerebral circulation, this increased pulsatility is associated with the white matter changes of cerebral small vessel disease, the leukoariosis visible on brain MRI, that represents the cumulative damage of years of excessive microvascular pulsatility. In the kidney, it contributes to the progressive glomerular injury of hypertensive nephropathy. The arterial stiffness that accompanies aging is thus not merely a risk factor for large vessel disease, but a direct cause of the microvascular organ damage of hypertension through the transmission of the cardiac pulse wave to organs that evolved to receive a dampened, smooth flow. The blood flow through the gastrointestinal tract, the splanchnic circulation, comprising the celiac, superior mesenteric, and inferior mesenteric arteries, and their tributaries, represents approximately 25% of resting cardiac output, and has the distinction of draining into the portal vein, rather than directly into the systemic venous circulation, delivering absorbed nutrients directly to the liver for processing. The portal circulation is one of the cardiovascular system's most important architectural specializations, the arrangement by which the blood, draining the intestine, stomach, and spleen, flows not directly into the systemic veins, but into the portal vein, and thence through the hepatic sinusoids, before reaching the hepatic veins and the inferior vena cava. This arrangement ensures that virtually everything absorbed from the gut passes through the liver before reaching the systemic circulation, a first-pass effect that allows the liver to process nutrients, converting amino acids, storing glucose as glycogen, metabolizing fatty acids, detoxify absorbed substances, removing gut-derived toxins, metabolizing many drugs, and absorb remnants of the chylomicrons before they reach peripheral tissues. The portal blood arrives at the liver with high concentrations of glucose, amino acids, and short-chain fatty acids following a meal, and the liver's first-pass metabolism substantially reduces these concentrations before the blood enters the systemic circulation. When the portal circulation is obstructed, as in cirrhosis of the liver, where the fibrotic replacement of the hepatic parenchyma impedes blood flow through the sinusoids, the portal venous pressure rises, producing portal hypertension. The blood seeks alternative routes from the portal system to the systemic veins, through portosystemic collaterals, the esophageal varices, the hemorrhoids, the caput medusae of dilated abdominal wall veins, and the sphenorenal shunts. The rupture of esophageal varices, thin-walled submucosal veins, in the lower esophagus, carrying the high portal pressure directly into the esophageal wall, can produce catastrophic, immediately life-threatening, upper gastrointestinal hemorrhage. The development of the cardiovascular system from the embryonic heart tube, which forms by fusion of the cardiac progenitor cells at approximately day 22 of gestation, begins beating at approximately day 23 and undergoes complex looping and septation to produce the four-chambered heart by the end of the 8th week, is one of the most precisely choreographed developmental sequences in biology. The development of the heart is remarkable not only for its result, but for its timing. The heart must become functional as an organ long before most of the rest of the organism has formed, because from the earliest days of its development, the embryo has grown beyond the size that can be sustained by diffusion alone and requires a circulatory system. The cardiac progenitor cells, derived from the splanchnic mesoderm of the lateral plate, migrate to the anterior part of the embryo and fuse at the midline to form the cardiac crescent, which then folds into the primitive cardiac tube. This tube begins beating at approximately 23 to 25 days of gestation, before the brain, before the limb buds, before any recognizable organismal structure exists, driven by the pacemaker activity of the myocardial cells that have already differentiated. The tube then undergoes cardiac looping, a rightward bending that establishes the definitive left-right asymmetry of the heart, followed by the complex remodeling and septation that over the next 4 weeks converts the single-chambered tube into the 4-chambered heart. The primary interatrial and interventricular septa grow in from the walls to divide the single atrium and the single ventricle. The atrioventricular and outflow valves form from endocardial cushion tissue. The outflow tract spirals to connect the aorta to the left ventricle and the pulmonary artery to the right. Each of these steps requires specific molecular signals, transcription factors, growth factors, signal transduction pathways, and their disruption produces the congenital heart defects that affect approximately 8 per 1,000 live births. The peripheral arterial disease of atherosclerosis in the lower limb arteries, producing the claudication pain of ischemic muscle during walking, follows the same pathophysiology as coronary artery disease, but in a different vascular bed, and its presence is a powerful marker of systemic atherosclerosis and of the elevated risk of myocardial infarction and stroke. Peripheral arterial disease, the atherosclerotic occlusion of the arteries supplying the legs, is the leg's equivalent of coronary artery disease, and like its coronary counterpart, it is a systemic disease, localized to a particular vascular bed. The same risk factors, smoking, diabetes, hypertension, hypercholesterolemia, drive the development of plaques in the femoral, popliteal, and tibial arteries that progressively narrow the lumen and reduce the blood supply to the leg muscles. At rest, the reduced supply may be adequate. The resting metabolic demands of leg muscle are modest. During walking, when the metabolic demand of the working muscle rises, the fixed stenosis cannot provide the required increase in flow. The oxygen debt in the ischemic muscle produces the accumulating, cramping pain of claudication, typically in the calf, for femoral or popliteal disease, in the thigh for iliac disease, that forces the patient to stop after a predictable walking distance. Rest allows the metabolic byproducts to clear, and the pain resolves, only to recur at the same walking distance. The ankle brachial index, the ratio of the systolic blood pressure at the ankle to the brachial artery, is the primary diagnostic test for peripheral arterial disease. Normal is approximately 1, and values below 0.9 indicate significant arterial disease. The importance of diagnosing peripheral arterial disease extends beyond the legs. The presence of significant atherosclerosis in the peripheral arteries is highly predictive of atherosclerosis in the coronary and cerebral circulation. A patient with claudication has a cardiovascular mortality rate that is 2 to 3 times that of an age-matched person without peripheral arterial disease. The development of interventional cardiology, beginning with Andreas Gruenzig's first coronary angioplasty in 1977, and progressing to the current era of drug-eluting stent implantation and transcatheter valve replacement has transformed the management of coronary artery disease and valvular heart disease from predominantly surgical to predominantly catheter-based treatment. The idea that a coronary artery occlusion could be treated by dilating it from the inside with a balloon catheter, without open surgery, without cardiopulmonary bypass, without the mortality of cardiac surgery, must have seemed improbable before Andreas Gruentzig performed the first percutaneous transluminal coronary angioplasty in Zurich on September 16, 1977. The patient, a 38-year-old insurance salesman with significant left anterior descending artery stenosis, had agreed in the cardiac catheterization laboratory to proceed with the experimental procedure if Gruentzig judged it technically feasible. Gruentzig inflated a small balloon catheter across the stenosis, dilating the artery and restoring flow. The patient walked out of the hospital 2 days later and remained free of symptoms for several years. The subsequent development of coronary stents, metallic scaffolding deployed within the dilated stenosis to prevent the elastic recoil and restenosis, that limited plain balloon angioplasty, and then of drug-eluting stents that release anti-proliferative agents to prevent the neo-intimal hyperplasia of bare metal stents, has produced the modern percutaneous coronary intervention that can restore flow to an acutely occluded coronary artery in approximately 30 to 60 minutes, potentially saving the myocardium that would otherwise be lost. The extension of this catheter-based approach to structural heart disease, transcatheter aortic valve replacement for the elderly and high-risk patients with severe aortic stenosis, transcatheter mitral valve repair, and catheter-based closure of congenital defects, represents the continuing evolution of a revolution that began with a single patient and a single balloon in 1977. The phenomenon of vascular calcification, the deposition of calcium phosphate mineral in the arterial wall, is not simply the passive precipitation of calcium in damaged tissue, but an active, regulated process resembling skeletal mineralization, involving vascular smooth muscle cell transdifferentiation into osteoblast-like cells, and driven by the same molecular pathways as bone formation. The recognition that vascular calcification is an active biological process rather than passive calcium deposition transformed the understanding of this common and clinically significant finding. For decades, the calcification visible in atherosclerotic plaques and in the medial layer of arteries in diabetes and chronic kidney disease was regarded as a late-stage marker of advanced vascular disease, a tombstone indicating where a diseased vessel had been, rather than a process with its own molecular drivers and potential therapeutic targets. The discovery that vascular smooth muscle cells could undergo transdifferentiation, reprogramming their gene expression toward an osteoblast-like phenotype under conditions of oxidative stress, hyperphosphatemia, elevated glucose, and inflammatory signals, revealed that the same molecular machinery that deposits mineral in bone also deposits it in arteries. The transcription factor RUNX2, the master regulator of osteoblast differentiation, is expressed in calcifying vascular smooth muscle cells. Alkaline phosphatase and other bone matrix proteins accumulate in the vascular wall. Matrix vesicles, the same structures that initiate mineralization in the growth plate, bud from the surface of vascular smooth muscle cells, and nucleate calcium phosphate crystal formation. The physiological calcification inhibitors, Fetuin A and matrix GLA protein, are reduced in vascular tissue when conditions favor calcification, removing the brakes on the process. This active biology offers therapeutic targets, interventions that maintain the balance of calcification inhibitors, that prevent smooth muscle cell transdifferentiation, or that modulate the phosphate balance in kidney disease patients, may reduce the rate of vascular calcification. The Borg scale of perceived exertion, the subjective rating of exercise intensity, from 6 to 20, corresponding roughly to heart rate multiples of 10, demonstrates the tight integration between the cardiovascular system and the brain's perception of physical effort, with the central command signal from the motor cortex contributing to both the cardiovascular response to exercise and to the subjective sense of effort. Gunnar Borg's observation in the 1970s that subjects perceived exertion during exercise correlated remarkably closely with their heart rate, and that the Borg scale values approximately corresponded to heart rate when multiplied by 10, revealed something important about the relationship between cardiac and perceptual responses to exercise. The central command hypothesis that the motor cortex sends a signal not only to the working muscles, but simultaneously to the cardiovascular center in the medulla, producing anticipatory cardiovascular activation before any peripheral feedback signals could have arrived, explains why heart rate begins to rise within the first beat of exercise, and why imagined exercise or mental preparation raises heart rate. The perceived sense of effort during exercise is partly determined by the magnitude of this central command signal. The more motor units recruited, the stronger the central command, the greater the perceived exertion, regardless of the actual mechanical output of the exercise. This is why exercise feels harder when the muscles are fatigued, when the person is dehydrated, when they are hypoxic at altitude. In each case, more central command and more afferent feedback from the periphery is required to maintain the same mechanical output, and the perceived effort rises accordingly. The cardiovascular response to exercise, the heart rate, the cardiac output, the blood pressure, is not simply the body's response to the metabolic needs of the muscles. It is also the body's response to the brain's commands, anticipating and supporting the motor effort that the brain is planning and executing. The role of the cardiovascular system in temperature regulation during exercise, vasodilating the skin circulation to radiate heat, while simultaneously maintaining the blood flow to to working muscles requires a careful cardiovascular balance that can be compromised by dehydration, as the competing demands of thermoregulation and exercise hyperperfusion stress the cardiac output capacity. During prolonged exercise in warm conditions, the cardiovascular system faces two simultaneous and potentially competing demands. The working muscles require blood flow for oxygen delivery and metabolite removal, and the skin requires blood flow to carry the body's heat to the surface, where it can be radiated and evaporated. At mild exercise in cool conditions, these demands are easily met by the elevated cardiac output of exercise. As exercise intensity increases, as the environment warms, and particularly as dehydration reduces the plasma volume, the cardiovascular system approaches the limits of its capacity to fulfill both requirements simultaneously. Dehydration, through sweat loss that is not adequately replaced, reduces plasma volume, reducing venous return, and therefore the cardiac preload that drives the Frank-Starling mechanism. The reduced preload compromises stroke volume, and heart rate must rise to compensate, approaching the maximum and limiting the cardiac output reserve. As the cardiac output reserve shrinks, the competition between muscle blood flow and skin blood flow becomes acute. Skin blood flow may be curtailed to maintain muscle perfusion, allowing body temperature to rise, or muscle blood flow may be maintained, allowing dehydration and cardiovascular strain to accelerate. The deterioration of exercise performance in the heat and with dehydration reflects this cardiovascular limit. The heart has reached the boundary of what it can do simultaneously. Adequate hydration before and during prolonged exercise in the heat is not merely comfort, it is the maintenance of the plasma volume that allows the heart to meet both the thermoregulatory and the exercise demands without approaching its capacity limit. The blood flow to the brain, cerebral blood flow, is maintained at approximately 50 milliliters per 100 grams per minute across a wide range of arterial pressures by the cerebral autoregulation mechanism, and its disruption in hemorrhagic and ischemic stroke represents the most clinically urgent failure of local vascular regulation in medicine. Cerebral blood flow is, in the hierarchy of circulatory priorities, at the very top. The brain consumes approximately 20% of the body's oxygen, despite being 2% of its weight, and its neurons can tolerate only 4 to 5 minutes of complete ischemia before suffering irreversible injury. The cerebral autoregulation that maintains constant flow across mean arterial pressures from 50 to 150 millimeters of mercury is the primary protection against the cardiovascular fluctuations of daily life. The mechanisms of this autoregulation include the myogenic response of the cerebral arterioles, the metabolic response to local changes in CO2 and oxygen tension, and the neurogenic control through autonomic innervation. In ischemic stroke, the occlusion of a cerebral artery by thrombosis or embolism, the territory downstream of the occlusion is immediately deprived of blood, and the cells there begin to die within minutes, unless collateral flow can be established or the occlusion reversed. The therapeutic window for effective reperfusion by intravenous thrombolysis or mechanical thrombectomy is measured in hours every 30 minutes of treatment delay in ischemic stroke is associated with additional neurological disability in the treated population, expressing the time dependency of brain tissue ischemia in a phrase that has become a motto of stroke treatment: time is brain. In hemorrhagic stroke, the rupture of a vessel into the brain parenchyma or subarachnoid space, the expanding hematoma directly damages brain tissue and raises intracranial pressure, compressing the surrounding brain and threatening the herniation of the brainstem through the foramen magnum. That is one of medicine's most feared events. The coagulation system's activity is elevated during cardiovascular disease and the inflammation of atherosclerosis, contributing to the prothrombotic state that underlies the risk of acute coronary events, and the measurement of D-dimers, fibrin degradation products, from plasmin-mediated fibrinolysis, provides a sensitive biomarker of pathological thrombus formation. D-dimers are the fragments produced when plasmin cleaves the cross-linked fibrin of a thrombus, named for the D-domain of fibrin, and the fact that they arise from the degradation of cross-linked fibrin dimers. Their measurement in blood provides a sensitive indicator of ongoing thrombus formation and fibrinolysis. When a thrombus is present, fibrinolysis is simultaneously activated, and D-dimers are continuously produced. In the clinical context of suspected venous thromboembolism, deep vein thrombosis, or pulmonary embolism, a negative D-dimer test has a very high negative predictive value if the D-dimer is below the threshold. In a patient with low pretest probability, venous thromboembolism is effectively excluded, and no imaging is required. This diagnostic strategy, D-dimer followed by imaging only if positive, is one of the most evidence-based in emergency medicine and avoids the unnecessary irradiation of CT pulmonary angiography in the majority of patients presenting with possible pulmonary embolism. The D-dimer's limitation is its poor specificity. It is elevated in many conditions where coagulation is activated: surgery, infection, inflammation, malignancy, pregnancy, and in the elderly population, where most suspected PE presence. A positive D-dimer therefore requires imaging confirmation, but its sensitivity makes it invaluable. As a rule-out test, a normal D-dimer in a patient with low pretest probability is one of emergency medicine's most reassuring results. The heart's intrinsic contractility is modulated by the calcium transient, the rise and fall of intracellular calcium that triggers and terminates each contraction, and its augmentation by sympathetic stimulation through the beta-1 adrenergic receptor. Cyclic AMP protein kinase A pathway is the molecular basis of the increased contractility of exercise and of inotropic drug therapy. The calcium transient of the cardiomyocyte, the brief rise in cytoplasmic calcium concentration from approximately 100 to approximately 1000 nanomolar with each action potential is the molecular switch that turns the contractile apparatus on for each beat and often the subsequent relaxation. The amplitude of the calcium transient, the peak concentration reached, determines the degree of myofilament activation and therefore the strength of the contraction, which is why contractility can be increased by increasing the peak calcium transient. The beta-1 adrenergic receptor, activated by noradrenaline from sympathetic nerve terminals, or adrenaline from the adrenal medulla, couples through GS protein to adenylyl cyclase, increasing cyclic AMP and activating protein kinase A. pKa phosphorylates multiple targets, the L-type calcium channel, increasing the trigger calcium influx that initiates calcium-induced calcium release from the sarcoplasmic reticulum, the ryanodine receptor of the sarcoplasmic reticulum, increasing its open probability, and the amplitude of calcium release, phospholambin, the regulatory protein that inhibits SERCA, the calcium pump of the sarcoplasmic reticulum, reducing its inhibitory effect and accelerating calcium reuptake. The combined effects increase the peak calcium transient, increase the rate of calcium removal, and therefore increase both the strength of contraction and the speed of relaxation, exactly the properties required for the increased heart rate and stroke volume of the exercise response. Inotropic drugs, digoxin, dobutamine, milrinone, each augment the calcium transient by different mechanisms, providing pharmacological tools for the management of acute and chronic heart failure. The renal contribution to long-term blood pressure regulation through the kidney's control of extracellular fluid volume and the pressure-natriuresis relationship is so fundamental that all forms of sustained hypertension ultimately require the kidney's complicity. The kidney has been shifted to a higher pressure set point and is retaining more sodium at that pressure than it should. Arthur Guyton's pressure-natriuresis relationship, the observation that the healthy kidney increases its sodium and water excretion as arterial pressure rises and reduces it as pressure falls, creating a powerful long-term blood pressure control, is the theoretical foundation for understanding the kidney's role in hypertension. In a person with normal blood pressure, the kidney's urinary sodium output exactly matches dietary intake. At the normal blood pressure set point, the system is in equilibrium. In hypertension, whatever its proximate cause, the kidney is excreting less sodium at the prevailing blood pressure than it should. It requires the higher pressure to achieve the sodium balance that a normal kidney would achieve at lower pressure. This rightward shift of the pressure-natriuresis curve, requiring a higher pressure for the same sodium excretion, is the kidney's contribution to the maintenance of hypertension. The mechanisms producing this shift include the activation of the renin-angiotensin-aldosterone system, which directly increases tubular sodium reabsorption, increased sympathetic tone to the kidney's tubular cells, which also promotes sodium retention, and the intrarenal structural changes of hypertension itself. including the nephrosclerosis that reduces the glomerular filtration area. Every antihypertensive drug ultimately lowers blood pressure, at least in part, by shifting the pressure natriuresis curve back toward normal, by removing the factor that was requiring the kidney to retain excess sodium at the prevailing pressure. The concept of the cardiac reserve, the difference between resting and maximal cardiac output, determines the capacity for physical activity and the margin of safety in the face of cardiovascular disease, and its measurement through cardiopulmonary exercise testing provides some of the most prognostically valuable information in cardiovascular medicine. The maximal oxygen consumption, VO2 max, is the gold standard measure of cardiovascular fitness and is the product of the maximal cardiac output and the maximal arteriovenous oxygen difference. In young, healthy adults, VO2 max may be 35 to 45 milliliters per kilogram per minute. In elite endurance athletes, it may exceed 70 milliliters per kilogram per minute, reflecting both their high maximal cardiac outputs and their well-trained muscles' ability to extract oxygen efficiently. In sedentary elderly adults, it may fall below 20 milliliters per kilogram per minute. The rate of decline in VO2 max with age, approximately 1% per year from young adulthood, is a consequence of both the age-related decline in maximal heart rate and the age-related reduction in stroke volume capacity, and it represents the progressive narrowing of the cardiac reserve between resting and maximal capacity. The cardiopulmonary exercise test, which measures VO2, VCO2, ventilation, heart rate, and blood pressure continuously during incremental exercise to maximum, provides a comprehensive assessment of the cardiovascular, pulmonary, and muscular systems' integrated response to exercise. A VO2 max below 14 to 16 milliliters per kilogram per minute in a heart failure patient is associated with very poor prognosis and has traditionally been used to identify patients who might benefit from cardiac transplantation. The anaerobic threshold, the VO2 at which metabolic acidosis begins, indicating that aerobic metabolism can no longer keep pace with exercise demands, is a reproducible submaximal marker of cardiovascular fitness that does not require maximal effort. The structure of the myocardial wall, the ventricular myocardium arranged in helical sheets of muscle fibers that wrap the ventricle from apex to base in a double helix pattern, allows the complex twisting and untwisting motion of ventricular contraction and relaxation that contributes substantially to the ejection of blood and the suction of ventricular filling. The ventricular myocardium is not simply a uniformly contractile structure. It is a precisely organized architecture of muscle fibers, arranged in sheets whose orientation varies systematically through the wall thickness, from approximately 60 degrees counterclockwise from the long axis at the epicardium to approximately 60 degrees clockwise at the endocardium. This crossing helical arrangement is the mechanical basis of the ringing, twisting motion of systole and the untwisting of diastole, that can be imaged by cardiac MRI. During systole, the epicardial and endocardial layers pull in opposite rotational directions, producing the apical counterclockwise rotation and basal clockwise rotation visible. In 4-chamber cardiac MRI, the systolic twist that squeezes the ventricle more effectively than simple shortening could. During early diastole, the stored elastic energy in the myocardium drives the rapid unwinding, the diastolic untwist, that produces the suction effect responsible for the rapid early filling of the left ventricle. This elastic recoil, the ventricles spring back from the compressed, twisted systolic configuration, actively draws blood in from the atrium during the early filling phase, contributing to the rapid filling of the ventricle at lower atrial pressures. The architectural organization of the ventricular myocardium is not incidental. It is the engineering solution that allows the ventricle to develop high pressures through cross-fiber interaction, while also producing the twisting motion that maximizes ejection efficiency and the elastic recoil that facilitates filling. Diseases that alter the architecture, the fibrosis of cardiomyopathy, the regional dysfunction of infarction, disrupt the coordinated twist and impair both ejection and filling. The measurement of cardiac troponin has revealed that a condition called myocardial injury with non-ischemic cause, troponin elevation without obstructive coronary artery disease, is common in hospitalized patients and carries significant prognostic implications, expanding the clinical understanding of myocardial injury beyond the classical paradigm of coronary thrombosis. Before the widespread use of high-sensitivity troponin assays, the clinical detection of myocardial injury was largely confined to the acute coronary syndromes, the presentations of coronary thrombosis, and the troponin measurement was primarily used to diagnose or exclude myocardial infarction. High-sensitivity troponin assays, capable of detecting troponin at femtomolar concentrations, revealed that myocardial injury, defined as a troponin above the 99th percentile of a reference population, was present in a much wider range of conditions than previously recognized: severe sepsis, pulmonary embolism, myocarditis, stress cardiomyopathy, Takotsubo syndrome, cardiac contusion, cardiotoxic chemotherapy, high-degree atrioventricular block, and the chronic myocardial stress of hypertension and hypertrophic cardiomyopathy. The recognition that elevated troponin could occur in the absence of obstructive coronary disease, and that many patients admitted to general medical wards had elevated troponins as markers of their underlying systemic illnesses' cardiovascular impact, created a new category of cardiac diagnosis and a new clinical challenge: the interpretation of troponin elevation in a patient who does not have an acute coronary syndrome. The prognosis of patients with non-ischemic myocardial injury is often poor, reflecting the severity of the underlying condition, but the management implications are different from those of acute myocardial infarction. The high-sensitivity troponin assay did not merely improve the diagnosis of heart attacks. It revealed the pervasiveness of myocardial injury across the spectrum of serious illness. The normal range of resting cardiac output, 4 to 8 liters per minute, can be exceeded by the high output states of severe anemia, thyrotoxicosis, arteriovenous fistula, and Paget's disease of bone, in which reduced oxygen carrying capacity or reduced peripheral resistance drives a compensatory increase in cardiac output that can, over time, produce high-output heart failure. High-output heart failure, the rare but important condition in which the heart fails not because its output is too low, but because the required output is too high, represents the cardiovascular system working at the edge of its capacity to satisfy an abnormally high demand. In severe anemia, the reduced oxygen content per milliliter of blood requires a compensatory increase in flow to maintain oxygen delivery. The heart must pump more liters per minute to deliver the same total oxygen, achieving this through tachycardia and increased stroke volume. In thyrotoxicosis, the excess thyroid hormone increases the metabolic rate of every tissue in the body, including the heart, and the increased oxygen demand of the periphery drives a compensatory increase in cardiac output. Arteriovenous fistula, either a surgically created access site for hemodialysis or the result of a traumatic or congenital arteriovenous connection, short-circuits the normal high-resistance path of the arterial blood through the capillaries, allowing blood to flow directly from artery to vein at high pressure, reducing the effective systemic vascular resistance and requiring the heart to pump more to maintain the same tissue perfusion. Over time, the sustained demand for a high cardiac output produces the same pathological cardiac hypertrophy and eventual decompensation as pressure overload through the volume-mediated mechanical stress on the ventricular wall. Recognition of the high output state is essential because the treatment is directed at the underlying cause, correcting the anemia, treating the thyrotoxicosis, ligating the fistula, rather than at the heart failure itself. Stay a while longer. You have stayed with me a very long time tonight. Through the 4 chambers and the 2 circulations, and the electrical cascade, and the blood's journey, from the heart to the capillaries and back again. Through the chemistry of clotting, and the biology of the endothelium, and the physics of pressure and flow. 100 facts about the system that has been sustaining you through every moment of your life, and you have been here for almost all of them. I do not take that lightly. Time is the most honest gift there is. If Relax with Science has earned a small place in your evenings, if these nights have given you something you would like to return to, subscribing is the simplest and most honest way to say so. I will be here. I always will be. Just a little further now. The heart is slowing. We are almost where we are going. You have stayed with me a very long time tonight. Through the 4 chambers and the 2 circulations, and the electrical cascade, and the blood's journey, from the heart to the capillaries and back again. through the chemistry of clotting, and the biology of the endothelium, and the physics of pressure and flow. 100 facts about the system that has been sustaining you through every moment of your life, and you have been here for almost all of them. I do not take that lightly. Time is the most honest gift there is. If Relax with Science has earned a small place in your evenings, if these nights have given you something you would like to return to, subscribing is the simplest and most honest way to say so. I will be here. I always will be. Just a little further now. The heart is slowing. We are almost where we are going. The phenomenon of cardiac hypertrophy, both the physiological hypertrophy of the athlete's heart and the pathological hypertrophy of pressure overload, involves the same initial molecular signaling, but diverges in its downstream effects, with physiological hypertrophy maintaining normal cardiac geometry and function, and pathological hypertrophy progressively impairing diastolic function, and ultimately ejection fraction. The distinction between physiological and pathological cardiac hypertrophy has occupied cardiovascular researchers for decades, because the same initial stimulus, increased mechanical stress on the cardiomyocytes, triggers what appear to be overlapping, but ultimately divergent molecular responses. In athletes, the sustained increases in cardiac output during training produce the increased preload and afterload that drive myocyte elongation, chamber dilation, and modest wall thickening, the eccentric hypertrophy pattern, associated with preserved ejection fraction, normal diastolic function, and a cardiac geometry suited to high stroke volumes. The molecular signature of physiological hypertrophy features activation of the PI3K-ACT-mTOR pathway, the same growth pathway activated by IGF-1, and the maintenance of a normal or near normal gene expression profile in the cardiomyocytes. In pathological hypertrophy, from hypertension, aortic stenosis, or hypertrophic cardiomyopathy, the sustained pressure overload activates primarily the calcineurin NF-AT pathway and the MAPK pathway, driving a fetal gene expression reprogramming, in which the cardiomyocytes revert to expressing the slower, less efficient myosin heavy chain isoforms. The faster calcium handling proteins are reduced, and the metabolic profile shifts from the fatty acid oxidation of the normal adult heart toward the less efficient glucose metabolism of the fetal heart. The structural result is a thickened, stiffer, less compliant ventricle, the concentric hypertrophy, in which diastolic filling is progressively impaired. Same initial trigger, different molecular pathway, different structural and functional outcome. The heart adapts to what the body asks of it, but the terms of the adaptation matter. The systemic arterial tree's branching pattern, from the aorta through multiple generations of branching to the approximately 40 billion capillaries, follows a geometry that minimizes the cardiac work required to perfuse all tissues, with the branching angles and vessel diameters obeying Murray's law, which predicts that the cube of the parent vessel radius equals the sum of the cubes of the daughter vessel radii at each bifurcation. Murray's Law, formulated by Cecil Murray in 1926, predicts that the optimal geometry for a vascular network that must minimize both the work of driving blood through the vessels and the metabolic cost of maintaining the blood and vessel wall is one in which the cube of the parent vessel radius equals the sum of the cubes of the daughter vessel radii at each bifurcation. Our superscript 3 parent equals our superscript 3 daughter 1 plus our superscript 3 daughter 2. This simple relationship emerges from the optimization of two competing costs: the work of pushing blood through narrow vessels, which decreases as vessel radius increases, and the metabolic cost of maintaining the blood volume and vessel wall, which increases as vessel radius increases. The branching angle predicted by Murray's Law at each bifurcation, approximately 75 degrees between the two daughters for equal daughter vessels, minimizes the path length and therefore the resistance, while maintaining the metabolic cost within bounds. Remarkably, measurements of actual arterial branch angles and vessel diameters throughout the vascular tree of many species have confirmed that real vasculature approximates Murray's Law reasonably closely, particularly in the microcirculation where the design constraints are tightest. The violations of Murray's Law that occur in atherosclerotic disease, the stenoses, occlusions, and remodeled geometries of diseased vessels, produce local hemodynamic disturbances that further accelerate the disease through the endothelial dysfunction of disturbed flow. The original vascular geometry was optimized. Its disruption is self-reinforcing. The heart's ability to generate force is also influenced by its shortening velocity, the force-velocity relationship showing that force production falls as shortening velocity increases, and the power output of the heart, the product of force and velocity, is maximized at intermediate shortening velocities, with implications for the optimal hemodynamic conditions for cardiac efficiency. The force-velocity relationship of cardiac muscle, like that of skeletal muscle, is a hyperbolic inverse relationship at zero shortening velocity, isometric contraction. The force is maximum at maximum shortening velocity, zero load. Force is zero at intermediate velocities. Force is intermediate. The power output of the heart, the rate of doing mechanical work, which is force times velocity, is therefore maximized at intermediate loading conditions, neither at maximum load, where velocity falls to near zero, nor at minimum load, where force falls to near zero. This optimal loading condition for cardiac power output, approximately 1/3 of the maximum isometric pressure, corresponds approximately to the normal afterload conditions in which the heart operates, suggesting that the normal systemic vascular resistance is reasonably close to the optimal loading for maximal cardiac efficiency. In heart failure, the elevated systemic vascular resistance of the neurohumoral response shifts the operating point toward higher afterload, moving the heart away from its optimal loading and reducing its power output efficiency, which is one of the mechanisms by which vasodilators improve cardiac function in heart failure. The reduction in afterload by ACE inhibitors, angiotensin receptor blockers, and nitrates moves the heart back toward more favorable loading conditions, allowing it to develop more of its available power at the pressures it is now asked to generate. The endocardium, the smooth inner lining of the heart chambers, is a specialized endothelium that not only provides the non-thrombogenic surface in contact with the blood within the heart, but also regulates cardiomyocyte function through the release of nitric oxide, endothelin, and other paracrine signals, constituting an endocardial-myocardial signaling axis, analogous to the endothelial smooth muscle axis of the blood vessels. The endocardium has long been regarded as simply the smooth inner surface of the cardiac chambers, a surface whose primary purpose was to present a non-thrombogenic lining to the blood within the heart, analogous to the endothelium of blood vessels. The discovery that endocardial endothelial cells are not merely passive liners, but active secretory cells that produce nitric oxide, endothelin, prostaglandins, and other vasoactive substances, and that these substances directly regulate the contractility and relaxation of the underlying cardiomyocytes, revealed an endocardial-myocardial signaling axis of considerable functional importance. Nitric oxide produced by the endocardium, particularly in response to increased filling pressure and shear stress on the endocardial surface, reduces myocardial contractility through a cyclic GMP-dependent mechanism, providing a mechanism by which the heart can sense its own filling state and modulate its contractility accordingly. Endothelin produced by the endocardium stimulates cardiomyocyte hypertrophy through its receptor on the cardiomyocyte surface, a pathway implicated in the pathological hypertrophy of sustained pressure overload. The endocardium is physically closest to the subendocardial cardiomyocytes, the same layer that is most vulnerable to ischemia, most densely supplied with conduction tissue, and most exposed to the mechanical stresses of high filling pressures. The endocardial signals that regulate cardiomyocyte function are not uniformly distributed through the myocardial wall, but are concentrated in the subendocardial region, potentially contributing to the known heterogeneity of myocardial function between the subendocardial and epicardial layers. The global cardiovascular disease burden. Cardiovascular diseases causing approximately 18 million deaths per year worldwide, accounting for approximately 32% of all global mortality, reflects both the universality of the underlying biological risk factors and the success of risk factor modification and treatment in progressively reducing the age-specific mortality of these conditions in high-income countries. The global burden of cardiovascular disease is simultaneously a story of biological vulnerability and of the remarkable progress that evidence-based prevention and treatment have achieved in reducing that vulnerability's consequences. The biological vulnerability. The human cardiovascular system's susceptibility to atherosclerosis, to hypertension, to the arrhythmias of an aging heart, to the heart failure that follows decades of metabolic stress, is universal and only partially modifiable. But the modification that is possible has been dramatic in high-income countries over the past 50 years. The age-specific mortality from coronary artery disease and stroke has fallen by approximately 60 to 70%. The reduction reflects, in roughly equal measure, the reduction in smoking prevalence, the most important preventable cardiovascular risk factor, the improved treatment of hypertension and hypercholesterolemia, and the dramatic improvement in acute care of myocardial infarction and stroke through reperfusion therapy, antiplatelet agents, and statins. The improvement in survival after myocardial infarction has been particularly striking. The hospital mortality from acute myocardial infarction in the era before coronary care units was approximately 30%. With modern reperfusion therapy, it has fallen to below 5%. This progress has not been uniform. Cardiovascular mortality has fallen more slowly in low and middle-income countries, where the risk factor burden is rising due to urbanization, dietary change, and reduced physical activity, and where the healthcare systems for acute treatment are less developed. The global cardiovascular disease burden remains the leading cause of death because the world's population is aging and because the metabolic risk factors of obesity, diabetes, and hypertension are increasing worldwide. The Doppler echocardiogram, the imaging modality that uses ultrasound to measure the velocity of blood flow through the heart and across valves, can non-invasively quantify the severity of valvular stenosis and regurgitation, estimate filling pressures and cardiac output, and detect regional wall motion abnormalities that indicate myocardial ischemia, making it the most versatile diagnostic tool in cardiology. The Doppler echocardiogram is to cardiology what the physical examination of the heart was before imaging, a method of directly observing the structure and function of the heart, but with a resolution, quantitativeness, and freedom from the limitations of external auscultation that makes it transformatively more powerful. The physical basis is the Doppler effect. When ultrasound waves strike moving red blood cells, the reflected frequency is shifted by an amount proportional to the velocity of the cells, allowing the velocity of blood flow at any point in the heart to be calculated from the measured frequency shift. The continuous wave Doppler mode measures the peak velocity of blood flow through stenotic valves, from which the pressure gradient can be calculated using the Bernoulli equation. A velocity of 4 meters per second across the aortic valve corresponds to a pressure gradient of 64 millimeters of mercury, indicating severe aortic stenosis. The pulsed wave Doppler mode measures velocity at a specific depth, allowing the characterization of the filling pattern of the left ventricle, the ratio of early to late filling velocities, the deceleration time, the tissue Doppler velocity of the mitral annulus, that together define the diastolic function of the heart and estimate the filling pressures. The color Doppler mode maps the velocity of blood flow across a two-dimensional field, revealing the regurgitant jets of incompetent valves, as flame-colored mosaics of turbulent retrograde flow. The combination of structural imaging, functional assessment, and hemodynamic quantification that the modern echocardiogram provides in a 30-minute, radiation-free examination has made it the indispensable tool of cardiovascular diagnosis. The concept of matched ventricular arterial coupling, the relationship between the elastic properties of the left ventricle and the impedance of the arterial system into which it pumps, determines the efficiency with which the heart converts its mechanical energy into stroke work, and its disruption in heart failure and hypertension is a mechanism of reduced cardiovascular efficiency. The heart and the arterial system into which it pumps are mechanically coupled, the ventricle pumping into the compliance and resistance of the arterial tree. The efficiency of this coupling, the fraction of the ventricle's total mechanical energy that is converted into stroke work rather than being stored in the arterial wall or dissipated, depends on the matching between the ventricle's elastance, stiffness and systole, and the effective arterial elastance, the impedance seen by the ventricle. Optimal coupling, maximal efficiency of energy transfer from ventricle to the circulation, occurs when the effective arterial elastance equals the end systolic elastance of the ventricle. In health, this matching is approximately maintained, and the heart operates near its optimal efficiency. In heart failure, the reduced end systolic elastance of the failing ventricle is incompletely matched by the usually elevated arterial elastance of the hypertensive, stiffened arterial system. The mismatch reduces efficiency and worsens the hemodynamic compromise. In the presence of arteriovenous fistula or severe aortic regurgitation, conditions where the effective arterial elastance is dramatically reduced, the mismatch in the opposite direction allows high stroke volumes, but at the cost of elevated cardiac output requirements. Therapeutic interventions that reduce arterial impedance, vasodilators, improve ventricular arterial coupling in heart failure, moving the system toward more efficient operation and improving cardiac output without increasing myocardial oxygen demand. The concept of coronary flow reserve, the ratio of maximal pharmacologically stimulated coronary blood flow to resting coronary blood flow, normally approximately 4 to 5 in healthy coronaries, is the functional measure of the coronary vasculature's capacity to increase supply during demand, and its reduction by either epicardial stenosis or microvascular disease predicts adverse cardiac outcomes. Coronary flow reserve is the functional expression of the coronary circulation's buffering capacity, the ratio between what the coronary arteries can provide at maximum dilation and what they are providing at rest. A normal coronary artery can increase its flow 4-fold or 5-fold in response to maximal vasodilatory stimulation through adenosine, dipyridamole, or exercise by dilating its arterioles maximally. This reserve is what allows the heart to increase its coronary blood flow dramatically during exercise without exhausting its supply. When an epicardial stenosis narrows the coronary artery, the microvascular resistance must be reduced, even at rest, to maintain the resting flow. The arterioles downstream of the stenosis are already partially dilated to compensate. The maximum flow that can be achieved with additional vasodilatory stimulus is therefore lower, and the coronary flow reserve is reduced. Coronary flow reserve below approximately 2 is considered physiologically significant. It means the coronary artery can increase its flow by no more than 2-fold under maximal stimulation, which is often insufficient to meet peak exercise demands without ischemia. The coronary flow reserve can also be reduced by microvascular disease, the diffuse disease of the coronary arterioles and capillaries that occurs in diabetes, hypertension, and after cardiac transplantation, without any epicardial stenosis. Measuring the coronary flow reserve by Doppler echocardiography, fractional flow reserve by coronary pressure wire, or by PET myocardial perfusion imaging, provides the functional information that guides revascularization decisions beyond the anatomical degree of stenosis. The heart's position in the mediastinum, slightly left of center, with its apex pointing down into the left, at approximately the level of the 5th intercostal space, at the midclavicular line, is the result of its leftward cardiac loop during embryological development and is the basis for the stethoscope placements and the surface anatomy of the cardiac examination. The location of the cardiac apex at the 5th intercostal space in the midclavicular line is the most important surface landmark in cardiac examination. It is where the clinician places the stethoscope to hear the apex beat, where a displaced apex beat signals cardiac enlargement, and where the low-frequency sounds of mitral valve disease are best heard in the left lateral decubitus position. The heart occupies the middle mediastinum, bordered anteriorly by the sternum, posteriorly by the esophagus and spine, and laterally by the pleural cavities in the lung. The pericardial silhouette on a chest radiograph, the cardiomediastinal contour visible on every routine chest X-ray, reflects the size and shape of the cardiac chambers and the great vessels, and the experienced radiologist reads this silhouette as a diagnostic text: the right heart border formed by the right atrium, the left heart border by the aortic knuckle above, the pulmonary artery trunk below it, the left atrial appendage in conditions where the atrium is enlarged, and the left ventricular border below. Enlargement of any chamber shifts its respective border outward. The cardiothoracic ratio, the ratio of the widest cardiac diameter to the internal thoracic diameter at the same level, is normally less than half, and its increase signals cardiomegaly. The heart's position in the chest, its specific orientation, its surfaces, its chambers and their projections, is the anatomical basis of every clinical examination, every radiograph, every echocardiogram, and every surgical approach to the heart. It is the geography within which all cardiac medicine takes place. The cardiovascular system is the body's river system, always moving, never resting, carrying the substance of life from the heart through every vessel to every cell and back again, and it's ceaseless, Faithful work is the physical expression of what it means for the body to be alive. And tonight, as you rest, it continues exactly as it has continued through every night of your life. Begin with the simplest version of this last fact. The heart is beating right now. Not as a metaphor, not as a sentiment, but as a physical fact, as real as the weight of the body against the surface that receives it, and the temperature of the air in the room, and the quality of the dark. The sinoatrial node fired approximately 1 second ago, and the one before that, and the one before that, in a sequence that has been unbroken since the 3rd week of embryonic development. The left ventricle just contracted and ejected 70-odd milliliters of blood into the aorta, which expanded to receive it and is now recoiling, driving the blood forward through the branching tree of arteries, toward every corner of the body. In the capillaries, in the 500 square meters of one-cell thick exchange surface, where the cardiovascular system does its actual work, oxygen is leaving the hemoglobin of passing red cells and diffusing into the surrounding cells, and carbon dioxide is diffusing in the opposite direction, and nutrients are being delivered and waste is being collected, quietly, continuously, without any awareness on the part of the cells that receive these gifts. In the heart itself, the coronary arteries are perfusing the myocardium that just contracted, almost entirely in diastole, the resting phase, using the pressure stored in the elastic aortic wall during systole to drive the flow in the moment of relaxation. And in the sinoatrial node, the funny current is running, the HCN channels open, the sodium and potassium flowing inward, the pacemaker potential rising toward the threshold for the next action potential. In approximately 1 second, the cycle will complete and begin again. It has never not begun again. Across the decades of a life, through every night, through every illness, through every extremity of emotion and exertion and rest, the heart has found a way to fire the next beat. Tonight is no different. The heart is not tired. It does not know how to be tired, in the way that the limbs and the mind know tiredness. It simply continues. And in its continuing, it makes everything else, the breath, the thought, the dream, the rest, possible. Let it continue. Let the river run. It has always known the way. The cardiovascular system you have been traveling through tonight is not separate from you. Every word of what you have heard describes what is happening right now, in the chest that rises and falls with each breath, in the pulse that persists in the wrist, in the neck, in the temples, felt or not felt, present in either case. The heart that has been discussed in 100 different ways tonight has been beating through all of them. It was beating when we talked about the sinoatrial node, and it was beating when we talked about the endothelium, and it was beating when we talked about the capillaries, reaching every cell in every corner of the body, with the oxygen those cells cannot live without. It has not stopped once. It will not stop tonight. It will continue doing what it does in the quiet hours. Slower now, more efficient, the parasympathetic system having gently asserted its claim over the sympathetic, the heart rate perhaps 50 or 60 beats per minute, as the body settles into the rest it has been approaching. Somewhere in the course of this long night together, the body has quietened. The muscles have released their holding. The breath has slowed to the rate that sleep requires. The blood pressure, a little lower than it was an hour ago, a little lower than it was at the peak of the day, has found its night register. The coronary arteries, perfusing the myocardium during the longer diastoles of the slower rate, are giving the heart its own quiet supply. The endothelium is producing its nitric oxide, maintaining the vessels in their dilated, relaxed, antithrombotic state. The entire cardiovascular system has adjusted itself to the conditions of the night, and this adjustment is not automatic, in the sense of being unimportant. It is the body's recognition that recovery requires conditions different from performance, and that providing those conditions is part of the system's work. The cardiovascular system at rest is not idle. It is restoring. This is relax with science, saying goodnight, and meaning it with the full weight of everything we have moved through together. The wonder of the cardiovascular system does not leave when the words stop. It remains in the beating that continues, in the sinoatrial nodes still firing, in the blood still flowing, in the 500 square meters of capillary surface, still exchanging the gases and nutrients of life with the cells they serve. You are not just someone who has heard about the cardiovascular system tonight. You are the system. You are the 100,000 daily beats, and the 5 liters per minute, and the elastic aorta, and the ventricular twist, and the coronary perfusion, and the endothelial nitric oxide. You are all of it, resting now, doing what the rest was always for. Let the heart do what hearts do. It has been doing it for as long as you have existed. It knows what it is doing, in the dark,